Welcome, fellow dreamer. Tonight, we journey through the grand story of astronomy, tracing humanity's timeless quest to understand the stars above and our place within the vast cosmos. This tale unfolds accompanied by soothing music and abstract imagery designed to reveal little-known wonders and fascinating discoveries that will gently feed your curiosity as you drift peacefully towards sleep. So take a deep breath, settle into comfort, and allow your mind and eyes to rest as the story of the heavens unfolds before you. The first human being to truly notice the stars has been lost to time, their name and face dissolved into the vast ocean of prehistory. Yet we can imagine them, perhaps 50,000 years ago, standing beneath a darkening sky as day surrendered to night. Above them, points of light gradually emerged from the deepening blue, scattered across the heavens in patterns that must have seemed both random and strangely familiar. For our earliest ancestors, the night sky was not a distant abstraction, but an intimate companion. Without the glow of cities to wash away the stars, without walls to block the horizon, those ancient people experienced a celestial display we can scarcely comprehend today. On a clear, moonless night, far from any settlement, the Milky Way would have stretched overhead like a river of light, and thousands upon thousands of stars would have created a dome of brilliance that made the darkness itself seem alive. At first, perhaps, the stars were simply there, noticed but not contemplated. Survival demanded attention to more immediate concerns: finding food, seeking shelter, avoiding predators. But humans possess a quality that sets us apart: a tendency to search for patterns, to find meaning in repetition. And the night sky, for all its apparent chaos, is built upon repetition. Night after night, the same configurations would appear. A group of bright stars here, a distinctive pattern there. These arrangements traveled together across the sky, maintaining their relationships to one another, even as they wheeled overhead. Someone observant would have noticed that certain patterns appeared in the east as darkness fell, climbed toward the highest point in the southern sky, then descended toward the west before dawn reclaimed them. The stars moved, but they moved together, as if painted on an enormous sphere that slowly rotated around the Earth. The moon presented a different kind of pattern, more complex and more intimate. Unlike the distant stars, the moon was clearly a disk, not a point of light. Its face changed through a reliable cycle, the slender crescent that appeared just after sunset, growing night by night into a bright circle that illuminated the landscape, then waning back through the phases until it disappeared entirely, only to return again. This lunar cycle took roughly 29 days, and it would not have taken long for people to connect this rhythm with the passage of time itself. As seasons turned, more subtle patterns would have emerged to those who watched carefully. The sun's path across the sky changed throughout the year. In summer, it rose high, creating long days and short nights. In the winter, its arc stayed low, and darkness claimed more hours. This annual rhythm was fundamental to survival for any people who needed to track when plants would bear fruit, when animals would migrate, when cold weather would arrive. Even more remarkable, certain stars appeared connected to the seasons themselves. A bright star might appear on the eastern horizon just before dawn at a particular time of year, serving as a herald for seasonal change. These heliacal risings, as they would later be called, provided reliable markers in an uncertain world. The stars became a calendar written across the sky, available to anyone with the patience to read it. The planets must have troubled these early observers. Most stars held their positions relative to one another, but a few bright wanderers refused to obey this rule. They moved against the background of fixed stars, traveling along a specific band of the sky, sometimes appearing in the evening, sometimes before dawn. Their motions were complex, occasionally even reversing direction, but they too followed patterns that repeated over months and years. Archaeological evidence suggests that humans were marking astronomical cycles far earlier than we once believed. Across Europe, scratched bones dating back more than 20,000 years display marks that appear to track lunar phases. These artifacts, weathered and fragmentary, hint at minds engaged in the systematic observation of celestial cycles. People were not merely noticing the sky, but actively recording what they saw, creating external memories to supplement their own. Standing stones and ancient monuments scattered across every inhabited continent bear witness to this growing astronomical awareness. These structures required enormous effort to construct, yet many display clear alignments with celestial events. The arrangement is too precise, too consistent to be accidental. Someone was watching the horizon, noting where the sun rose on the longest day of summer, or where certain stars appeared at significant moments. They were translating these observations into stone, creating lasting markers that connected Earth and sky. Navigation provided another compelling reason to study the heavens. For peoples who traveled across featureless landscapes or ventured onto the ocean, the stars offered reliable guidance. The northern sky contained a star that barely moved, remaining almost fixed while all others rotated around it. This celestial anchor provided a constant reference point. Other stars rose and set at predictable positions along the horizon, creating a compass available every clear night. The development of agriculture intensified the need for calendrical precision. Farmers required knowledge of when to plant and when to harvest. Mistakes in timing could mean starvation. The sky provided answers if one knew how to read them. The relationship between celestial cycles and earthly seasons became crucial knowledge, passed down through generations, refined through careful observation. Stories began to crystallize around the star patterns. The human mind seeks narrative, and the random scatter of stars could be organized into figures. Animals, heroes, objects. These constellations served as memory aids, making it easier to identify and discuss specific regions of the sky. But they were more than mere convenience. The stories embedded astronomical knowledge in cultural memory, ensuring that observations made by one generation could be transmitted to the next. As thousands of years passed, this accumulated knowledge became increasingly sophisticated. People understood that lunar months did not align perfectly with solar years. They developed ways to reconcile these cycles, adding extra months at intervals to keep calendars synchronized with seasons. They predicted eclipses, those dramatic moments when the sun or moon would be obscured, events that must have seemed both terrifying and profound. The sky had become a text, and humanity had learned to read it. From scattered observations to systematic tracking, from simple pattern recognition to complex calendrical systems, our ancestors transformed their relationship with the heavens. They had no telescopes, no scientific instruments beyond their own eyes and minds, yet they discovered fundamental truths about the cosmos. The stars wheeled in predictable patterns. The planets wandered but followed rules. Time itself could be measured in celestial cycles. This knowledge would become the foundation for something greater. In certain places, in civilizations with writing and mathematics, astronomical observation would transform from practical necessity into systematic science. The ancient Mesopotamians, watching these same stars from their cities in the fertile river valleys, would take the next great step in humanity's relationship with the cosmos, creating the first detailed catalogues of celestial events and establishing the mathematical frameworks that would echo through millennia. The rivers flowed through the flat plains between the Tigris and Euphrates, carrying precious water through a landscape where the sky stretched endlessly in all directions. In this land called Mesopotamia, meaning the place between rivers, civilizations rose that would transform humanity's relationship with the heavens above. Here, the Sumerians and later the Babylonians looked upward with purpose, turning casual observation into systematic study. The night sky over ancient Mesopotamia offered a spectacle of crystalline clarity, with little vegetation to obscure the horizon and air unpolluted by anything but occasional dust. The stars appeared in brilliant profusion. The people who cultivated these river valleys, building cities of mud brick and developing systems of writing, discovered that the sky was not merely beautiful, but useful in ways that went far beyond simple timekeeping. Around 4,000 years ago, Babylonian priests began keeping detailed records on clay tablets, marking down the positions of celestial bodies with remarkable dedication. These weren't occasional jottings, but systematic observations carried out night after night, year after year, generation after generation. They noticed that while most stars wheeled overhead in fixed patterns, 5 bright objects wandered against this stellar backdrop. These wanderers, which we now call planets, traced their own paths through specific regions of the sky. The Babylonians divided the band of sky through which the sun, moon, and planets traveled into 12 sections. This division gave birth to what we know as the zodiac, with each section associated with particular star patterns. The names they gave these constellations would echo through millennia, passed through Greek and Roman cultures to reach our modern era largely intact. The precision with which they tracked these divisions reveals a mathematical sophistication that still impresses scholars today. Perhaps nothing demonstrates Babylonian astronomical achievement more clearly than their ability to predict eclipses. By the 7th century before the Common Era, they had recognized the Saros cycle, a period of approximately 18 years, after which eclipses repeat in similar patterns. This discovery required not just careful observation, but the compilation of records spanning many human lifetimes. The clay tablets preserved their observations across the centuries, creating an astronomical archive that no previous culture had achieved. The Babylonians developed a numerical system well suited to astronomical calculation. Their base 60 mathematics, inherited from Sumerian predecessors, gave us the 60-minute hour and the 360-degree circle. This wasn't an arbitrary choice, but one that reflected the approximate number of days in a year and offered numerous factors for easy division. When tracking the gradual movements of planets across the sky, such mathematical tools proved invaluable. On tablets written in cuneiform script, the wedge-shaped impressions made by reed styluses pressed into soft clay, astronomers recorded not just observations, but also calculations. They developed mathematical techniques to predict where planets would appear in the sky months or even years in advance. These predictions served both practical and ceremonial purposes, helping to maintain calendars and providing insights that were believed to carry messages about earthly affairs. The planet Venus received particular attention in Mesopotamian astronomy. The brightest object in the sky after the sun and moon, Venus appears as both an evening and morning star, though the Babylonians eventually recognized these as the same celestial body. The Venus tablet of Amisaduqa, dating from the 17th century before the Common Era, records the rising and setting of Venus over a period of 21 years. This document represents one of the oldest preserved astronomical records, demonstrating how early these systematic observations began. Jupiter and Saturn, the giant planets that move slowly against the background stars, also featured prominently in Babylonian records. They track these planets' positions through the zodiacal constellations with enough precision that modern astronomers can use their observations to refine our understanding of ancient chronology. The mathematical models they created to predict planetary positions involved sophisticated arithmetic sequences and geometric relationships. The Babylonian approach to astronomy differed fundamentally from the philosophical speculation that would characterize Greek astronomy. Rather than building grand theories about why celestial bodies moved as they did, Babylonian astronomers focused on describing patterns and creating predictive models. They sought the mathematical relationships that would allow them to forecast celestial events, treating the sky as a complex system whose regularities could be captured in numerical tables. Their star catalogues grew increasingly comprehensive over the centuries. The MUL-APIN, a compendium of astronomical knowledge compiled around 1,000 years before the Common Era, lists stars, constellations, and provides instructions for using stellar risings and settings to mark the passage of the year. This text reveals how thoroughly the Babylonians had surveyed the visible heavens, organizing celestial objects into coherent systems of knowledge. The legacy of Mesopotamian astronomy extended far beyond the river valleys where it originated. When Greek scholars encountered Babylonian astronomical knowledge, they found mathematical techniques and observational records far more extensive than their own. This Babylonian wisdom flowed westward, influencing the development of Greek astronomy, and through that channel, eventually reaching Renaissance Europe. The clay tablets themselves proved remarkably durable. Unlike papyrus or parchment, which deteriorates with moisture and time, fired clay can survive for millennia when buried in dry soil. Thousands of tablets containing astronomical observations and calculations waited in the ruins of ancient cities, preserving knowledge that would eventually help modern scholars reconstruct ancient astronomical events and refine historical chronologies. As the night deepens around us, and we imagine those ancient observers scanning the heavens above their ziggurats and temples, we can appreciate how they transformed stargazing into science. They created the first systematic astronomical archive, developed mathematical techniques for prediction, and established traditions of observation that would be maintained for centuries. The celestial patterns they recognized, the mathematical relationships they discovered, and the methodical approach they pioneered laid foundations that subsequent cultures would build upon, carrying humanity forward in its eternal quest to understand the cosmos. Along the fertile banks of the Nile, where the rhythms of the river governed all life, the ancient Egyptians turned their gaze upward with a practical reverence that would shape one of history's most astronomically sophisticated civilizations. The connection between heaven and earth felt immediate here, where the annual flooding of the great river meant the difference between abundance and famine, and where the predictable movements of celestial bodies offered a reassuring counterpoint to the uncertainties of earthly existence. The Egyptians watched the sky with the careful attention of those whose survival depended on understanding nature's patterns. Among all the stars that wheeled overhead through the long desert nights, one commanded special attention. Sirius, which they called Sopdet, blazed brighter than any other star in their heavens. The priests and astronomers observed that this brilliant point of light disappeared from view for roughly 70 days each year, and its reappearance on the eastern horizon just before sunrise coincided remarkably with the beginning of the Nile's annual inundation. This heliacal rising of Sirius became a celestial herald of renewal, marking the start of their year and the coming of the floods that would deposit rich nutrients across the farmlands. This observation led the Egyptians to develop one of humanity's earliest solar calendars, a practical timekeeping system that divided the year into 12 months of 30 days each, with 5 additional days added to complete the cycle. While this 365-day calendar would slowly drift out of alignment with the true solar year, which runs slightly longer, it represented a remarkable achievement in astronomical record-keeping. The calendar helped organize agricultural activities, religious festivals, and administrative functions across a vast kingdom that stretched along the Nile for hundreds of miles. The Egyptian understanding of celestial movements found its most enduring expression in stone. The Great Pyramids of Giza, rising from the desert plateau with geometrical precision, embody astronomical knowledge translated into architecture. The Great Pyramid, built for the pharaoh Khufu around 2460 BCE, demonstrates an alignment with cardinal directions so accurate that it continues to impress modern surveyors. The structure's sides face almost exactly north, south, east, and west, with an error of only a small fraction of a degree. Achieving this precision without magnetic compasses required careful astronomical observation, likely using the circumpolar stars that never set below the horizon as they wheeled around the celestial pole. The pyramid's builders understood the night sky with an intimacy born of countless hours spent studying stellar positions. They may have used a technique involving a plumb line and observations of stars rising and setting at equal altitudes to establish true north. Or they may have tracked the circumpolar stars themselves. Whatever method they employed, the result speaks to a sophisticated grasp of celestial mechanics and the patience to implement that knowledge in monuments designed to last for eternity. Within these massive structures, shafts extend from the burial chambers at precise angles. And while scholarly debate continues about their exact purpose, some of these passages align with significant stars and constellations of the Egyptian heavens. The southern shaft from the King's Chamber in the Great Pyramid points toward where Orion's belt would have appeared in that era, a constellation the Egyptians associated with Osiris, the god of the afterlife and rebirth. Such alignments suggest that the pyramids were not merely tombs but cosmological instruments, connecting the eternal soul of the pharaoh with the eternal cycles of the heavens. The Egyptians divided the night sky into constellations that reflected their own culture and mythology, different from those the Mesopotamians had identified. They recognized groups of stars they called decans, 36 stellar configurations that appeared over the eastern horizon just before dawn at intervals throughout the year. These decans served as celestial clocks, helping to mark the passage of both the year and individual nights. Star charts painted on tomb ceilings and coffin lids show these constellations, preserving an astronomical tradition that helped guide both the living and the dead through their respective journeys. In their temples, priests maintained traditions of astronomical observation that served both religious and practical purposes. The temple at Karnak, one of the largest religious complexes ever built, incorporated astronomical alignments in its design. The main axis of the temple aligns with the sunset on the winter solstice, allowing light to penetrate deep into the sanctuary at this significant moment in the solar year. Such careful orientation required sustained observation and planning, demonstrating how thoroughly Egyptian astronomy had become woven into the fabric of their sacred architecture. The Egyptians also tracked the movements of planets, those wandering stars that moved against the background of fixed constellations. Though their planetary observations were less systematic than those of the Mesopotamians, they recognized these celestial travelers and incorporated them into their worldview. The planet Venus, visible as both morning and evening star, received particular attention, though the Egyptians may not have initially realized that the morning and evening appearances represented the same celestial body. Egyptian timekeeping extended beyond annual calendars to the measurement of hours themselves. They developed water clocks, devices that measured time's passage by the regulated flow of water from one vessel to another. These instruments allowed for time measurement even when clouds obscured the stars or during the brightness of day. The division of both day and night into 12 hours each, though of varying length depending on the season, represents another lasting contribution to how humanity structures time. The astronomical traditions of ancient Egypt emerged from a landscape where the sky stretched vast and clear, where the contrast between the narrow green ribbon of the Nile Valley and the endless desert created a natural observatory. Here, the connection between celestial patterns and earthly prosperity felt immediate and tangible. The star Sirius announced the floods. The sun's position marked the seasons, and the circumpolar stars wheeled eternally around the celestial pole like the eternal nature of the pharaoh's power and the gods themselves. As centuries passed and Egypt's civilization evolved through dynasties and foreign influences, this astronomical knowledge persisted, preserved in monuments that would outlast the culture that created them. When Greek scholars later came to Egypt, they encountered these ancient traditions and incorporated elements into their own developing understanding of the cosmos, creating connections between different streams of astronomical thought. that would continue flowing through history, like the great river that made Egyptian civilization possible. As the accumulated wisdom of Egypt flourished along the Nile, another civilization across the Mediterranean was beginning to ask questions of a different kind. The ancient Greeks approached the heavens not merely as timekeepers or agricultural guides, but as puzzles to be solved through reason and geometric elegance. Their philosophers and mathematicians would transform astronomy from a practical craft into a theoretical science, introducing ideas so radical that some would not resurface for nearly 2,000 years. In the gentle air of the Aegean Islands and the sun-warmed streets of cities like Athens and Alexandria, thinkers began to wonder about the fundamental nature of the cosmos itself. What was the true shape of the Earth beneath their feet? How far away were the celestial bodies that moved overhead? And perhaps most fundamentally, what occupied the center of all this cosmic motion? The Pythagoreans, followers of the mysterious mathematician and philosopher Pythagoras, were among the first to propose that Earth was a sphere rather than a flat disk. Their reasoning combined observation with aesthetic philosophy. They noticed that ships disappeared hull first over the horizon, that the shadow Earth cast on the moon during lunar eclipses was always circular, and that different stars became visible as one traveled north or south. But beyond these practical observations, they believed that the sphere was the most perfect geometric form, and surely the cosmos would prefer perfection. This marriage of observation and mathematical idealism would characterize Greek astronomical thinking for centuries to come. Aristotle, whose influence on natural philosophy would dominate Western thought for 2 millennia, developed a comprehensive model of the cosmos in the 4th century before the Common Era. In his vision, Earth rested immobile at the center of everything, a sphere of heavy elements naturally seeking the lowest position. Around this stationary Earth, he imagined a series of crystalline spheres, transparent and invisible, each carrying a celestial body. The moon occupied the nearest sphere. Then came Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, with the stars themselves fixed to the outermost sphere. These nested spheres rotated at different speeds, producing the complex motions observed in the night sky. For Aristotle, this arrangement made perfect sense according to the physics he had developed. Heavy things fell downward because they sought Earth's center, while light things like fire rose upward. The celestial realm, composed of a perfect 5th element called ether, was fundamentally different from the earthly realm of change and decay. The heavens were eternal and unchanging, moving in perfect circles, because the circle represented perpetual motion without beginning or end. Yet not all Greek thinkers agreed with this earth-centered vision. On the island of Samos, a mathematician named Aristarchus proposed something extraordinary around 270 before the Common Era. He suggested that the Sun, not Earth, stood at the center of things, and that Earth both rotated on its axis and revolved around the Sun. His reasoning came from attempting to measure cosmic distances. By observing the moon at half phase, when the angle between Sun and Moon, as seen from Earth, should be 90 degrees, he tried to calculate the relative distances to these two bodies. Though his measurements were imprecise, they convinced him that the Sun was much larger than Earth. And surely, he reasoned, the larger body should occupy the central position, while the smaller one moved around it. Aristarchus's heliocentric model was elegant and, as we now know, fundamentally correct. yet it convinced almost no one in his own time. The reasons for its rejection reveal much about the interplay between theory and observation in ancient astronomy. If Earth truly rotated on its axis, why didn't objects get left behind? Why didn't a powerful wind constantly blow from the east? And if Earth orbited the Sun, the nearby stars should show parallax, a slight shift in apparent position as our viewpoint changed throughout the year. No such parallax could be detected, and while we now know this is because stars are unimaginably distant, ancient astronomers quite reasonably took it as evidence that Earth must be stationary. Another brilliant mind, Eratosthenes, made a measurement around 240 before the Common Era that would demonstrate the power of Greek geometric thinking. He had heard that in the southern city of Syene, the sun stood directly overhead at noon on the summer solstice, shining straight down wells without casting a shadow. Yet in Alexandria, far to the north, vertical posts cast definite shadows at the same moment. If Earth was a sphere, this difference made perfect sense. The sun's rays, traveling in parallel lines across the vast distance from that celestial fire, would strike different parts of a curved Earth at different angles. Eratosthenes measured the shadow angle in Alexandria and found it to be about 1/50th of a circle. Therefore, the distance between Alexandria and Syene must represent 1/50th of Earth's full circumference. Knowing that distance from caravan travel reports, he calculated Earth's circumference at about 40,000 kilometers. This figure, achieved through pure geometry and simple observations, was remarkably close to the true value. Here was tangible proof that careful reasoning could reveal cosmic truths that direct observation alone could never provide. The Greek astronomer Hipparchus, working in the 2nd century before the Common Era, brought unprecedented precision to observational astronomy. He compiled catalogues listing the positions of more than 800 stars, measured the length of the year to within minutes of the correct value, and discovered the precession of the equinoxes, a slow wobble in Earth's orientation that takes 26,000 years to complete a cycle. This discovery came from comparing his careful observations with records made by astronomers over a century earlier. Such was the Greek commitment to preserving and comparing data across generations. To aid in these measurements, Greek astronomers developed sophisticated instruments. The astrolabe, which would evolve into many forms over the following centuries, allowed them to measure the positions and heights of celestial objects. The armillary sphere, a skeletal celestial globe made of metal rings representing the equator, ecliptic, and other reference circles, helped them visualize the geometry of the heavens. These tools transformed astronomy from an activity of naked eye observation into an instrumental science. The Greeks also grappled with the puzzle of planetary motion. Unlike stars, which maintained fixed patterns, the planets wandered against the stellar background, sometimes even appearing to reverse direction in retrograde motion. Explaining these loops and variations while maintaining the aesthetic requirement of circular motion proved challenging. Astronomers proposed increasingly complex arrangements of circles, introducing the concept of epicycles, smaller circles whose centers moved along larger circles called deferents. A planet traveled along its epicycle while the epicycle's center orbited Earth on the deferent. As the Greek world gave way to Roman dominance and the center of learning, shifted to great libraries in places like Alexandria. These geometric models grew ever more refined. The stage was being set for a comprehensive synthesis that would incorporate all this accumulated wisdom into a single mathematically sophisticated system. That achievement would come from a man working in Roman Egypt whose model would reign supreme for over 1,000 years, a framework so compelling that it would require new observations and revolutionary courage to finally overturn it. But that is a story for another night's rest, as the stars continue their patient wheel overhead. The Greek philosophers had proposed various models of the cosmos, debating whether Earth or the Sun held the central position, contemplating perfect circles and divine geometry. Yet as brilliant as these theoretical discussions were, they lacked the comprehensive mathematical framework that could truly predict where the celestial wanderers would appear in the night sky. This need for practical, predictive astronomy would be fulfilled by a man working in Roman Egypt during the 2nd century of the Common Era, a scholar whose name would become synonymous with geocentric cosmology for the next 1400 years. Claudius Ptolemy lived and worked in Alexandria, that great lighthouse of learning, where the library had once stood, and where Greek mathematical tradition merged with Egyptian observational records and Babylonian computational techniques. Though we know remarkably little about his personal life, Ptolemy left behind a monumental work that would shape astronomical understanding until the Renaissance. This treatise, which he called the Mathematical Systematic Treatise, would become known by its Arabic name, the Almagest, meaning the greatest. The challenge Ptolemy faced was both elegant and vexing. How could one create a system that preserved the fundamental Greek assumption that Earth rested motionless at the universe's center, while also accounting for the wandering planet's seemingly irregular movements across the heavens? The planets did not simply glide smoothly westward like the fixed stars. Mars sometimes brightened dramatically and appeared to reverse direction, moving eastward for weeks before resuming its westward journey. Venus and Mercury never strayed far from the Sun, swinging back and forth like pendulums. Jupiter and Saturn moved with stately slowness, but they too occasionally performed their retrograde dances. To explain these complex motions, Ptolemy refined and systematized ideas that earlier astronomers had proposed, creating a geometric masterpiece of wheels within wheels. Each planet moved along a small circle called an epicycle, while the center of that epicycle simultaneously traveled along a larger circle called a deferent. Imagine a point on a rolling wheel, tracing a looping path through space as the wheel itself moves forward, and you begin to grasp the beauty of this geometric construction. But Ptolemy's system contained further subtleties. He recognized that simple epicycles and deferents could not fully capture the planet's observed behaviors. So he introduced the eccentric, placing the center of each deferent slightly away from Earth's position. This meant planets traveled faster when nearer to Earth and slower when farther away, matching what observers actually saw in the night sky. Even this was not quite sufficient to produce predictions matching the careful observations recorded over centuries. Ptolemy added one more geometric device that would prove controversial in later ages: the equant point. For each planetary orbit, he designated a point positioned opposite Earth from the deferent center. From this equant point's perspective, the epicycle's center appeared to move at constant angular velocity. This was a remarkable mathematical innovation, though it troubled later scholars who felt it violated the Greek ideal of perfect uniform circular motion. The result of these layered geometric constructions was extraordinary. Ptolemy's system could predict planetary positions with impressive accuracy, accounting for retrograde motions, variations in brightness, and the differing speeds of planetary wanderings. The mathematics was sophisticated, involving careful trigonometry and the use of chord tables that Ptolemy compiled with meticulous precision. His model worked not just as a qualitative description, but as a computational tool that astronomers could use to calculate where Venus would appear on a particular evening, or when Mars would begin its next retrograde loop. The Almagest contained far more than just the planetary model. Ptolemy compiled a star catalogue listing over 1,000 stars, recording their positions and relative brightnesses. He explained how to construct astronomical instruments and described the mathematics needed to work with circles and spheres. He presented theories about the moon's motion, with its own epicycles accounting for the variations in lunar speed and distance that cause the moon's apparent size to change throughout the month. He also tackled the difficult problem of planetary distances. While he could not measure absolute distances, Ptolemy created a nested system where each planet's sphere fitted precisely around the one below it, from the moon closest to Earth, then Mercury, Venus, the Sun, Mars, Jupiter, and finally Saturn at the outermost edge of the planetary realm. Beyond Saturn lay the sphere of fixed stars, rotating daily to produce the familiar rising and setting of constellations. This orderly arrangement gave the cosmos a comprehensible structure, a hierarchy that seemed to reveal divine organization in the heavens. The geocentric model aligned naturally with everyday experience. People felt no motion beneath their feet, saw no winds that would surely blow if Earth hurtled through space, observed heavy objects falling downward toward what seemed obviously the universe's center. Ptolemy's system made mathematical sense of celestial motions, while preserving this intuitive understanding of Earth's special, stationary position. For more than a millennium, the Ptolemaic system would dominate astronomical thinking across multiple civilizations. Islamic scholars would translate the Almagest, refine its tables, and build observatories to test and improve its predictions. Medieval European universities would teach Ptolemy's cosmology as the foundation of natural philosophy. Astronomers would adjust the model's parameters, adding more epicycles or tweaking the equant positions to match increasingly precise observations. But the fundamental geocentric framework remained unchallenged as orthodoxy. The system's longevity testifies to its genuine explanatory power. This was not a crude or simple model, but a sophisticated mathematical construction that made accurate predictions and provided a framework for understanding celestial mechanics. Ptolemy had created a grand synthesis, gathering centuries of observations and theoretical insights into a comprehensive whole that served practical needs while satisfying intellectual requirements for geometric elegance. As the stars wheeled overhead, through generations of scholars studying Ptolemy's work, copying his tables, and teaching his system, the geocentric cosmos seemed permanently established as the true description of reality. Yet within this very success lay the seeds of future revolution. The model's growing complexity, with epicycles piled upon epicycles to account for ever more precise observations, would eventually prompt some thinkers to wonder whether nature truly operated through such elaborate celestial machinery, or whether perhaps a simpler arrangement might exist that human minds had not yet imagined. While Ptolemy's intricate system of epicycles and deferents dominated Western astronomical thinking, far to the east another great civilization pursued its own remarkable study of the heavens. China's astronomical tradition developed independently across thousands of years, creating methods and discoveries that would remain largely unknown to European scholars, until much later centuries brought these separate streams of knowledge together. The Chinese approach to astronomy carried a distinctive character, shaped by the needs and philosophy of the imperial state. Unlike their Mediterranean counterparts, who often pursued celestial knowledge for its own sake or for philosophical understanding, Chinese astronomers worked primarily as officials in the service of emperors. Their observations served a vital political purpose, for the emperor ruled under what was known as the mandate of heaven. Any unusual celestial event might signal heaven's displeasure with earthly governance, making accurate prediction and interpretation of astronomical phenomena a matter of political stability. This practical necessity drove Chinese astronomers to maintain meticulous records of celestial events with extraordinary consistency. Generation after generation of court astronomers documented what appeared in the sky above them, creating an unbroken chronicle that would eventually span more than 3,000 years. These records, preserved on bamboo strips, silk scrolls, and eventually paper, form one of the most valuable astronomical archives in human history. Among their most important contributions were the detailed accounts of guest stars, the Chinese term for stars that appeared suddenly where none had been visible before. Modern astronomers recognize these observations as records of novae and supernovae, stellar explosions so brilliant they can briefly outshine entire galaxies. The Chinese noted these appearances with precise dates and locations, describing how long each guest star remained visible and how its brightness changed over time. One particularly famous observation from the year 1054 described a guest star so bright it could be seen in daylight for 23 days. This event is now known to have been the supernova that created the Crab Nebula, and the Chinese records provide crucial historical data about this cosmic explosion. Comets too received careful attention from Chinese astronomers. They classified these wandering celestial visitors by appearance, creating categories based on the shape and direction of their tails. Rather than viewing comets with the superstitious dread common in many cultures, Chinese observers approached them as natural phenomena worthy of systematic study. Their records document hundreds of cometary appearances, including multiple sightings of what would later be recognized as Halley's Comet, with observations dating back to at least 240 BCE. The Chinese developed sophisticated instruments to aid their observations. The armillary sphere, a skeletal celestial globe consisting of metal rings representing important celestial circles, allowed astronomers to measure the positions of stars and planets with considerable precision. These elegant brass constructions could be quite large, with some specimens standing taller than a person. By aligning the rings and sighting along them, an observer could determine celestial coordinates and track the movements of heavenly bodies across the night sky. Chinese astronomers also created their own system for organizing the stars, dividing the sky into 28 lunar mansions corresponding to the moon's progression through its monthly cycle. These mansions served as celestial landmarks, allowing precise description of planetary positions and the location of unusual events. 3 enclosures near the celestial pole contain stars of particular importance, including those associated with the emperor and the imperial court, reflecting the intimate connection between celestial observation and earthly governance. The Chinese calendar system represented another monumental achievement, requiring constant astronomical attention. Unlike the solar calendar that would eventually become standard worldwide, the traditional Chinese calendar followed a lunisolar pattern, tracking both the moon's phases and the sun's annual journey. Keeping such a calendar accurate demanded precise knowledge of both lunar and solar cycles, as the months followed the moon, while the years needed to remain synchronized with the seasons. This calendrical responsibility fell to the Imperial Astronomical Bureau, where teams of officials performed the complex calculations necessary to predict the exact moments of new moons, solstices, and equinoxes. Publishing the calendar for the coming year stood as one of the emperor's sacred duties, a demonstration of his harmony with celestial order. An error in the calendar or a failure to predict an eclipse could undermine confidence in the emperor's mandate to rule, making the astronomer's work carry enormous consequences. The prediction of eclipses received particular emphasis. Chinese astronomers developed methods to forecast both solar and lunar eclipses with impressive reliability. They understood that eclipses followed patterns, with similar eclipses occurring at regular intervals. By studying their extensive historical records, they identified these cycles and used them to anticipate future events. When an eclipse occurred exactly as predicted, it demonstrated the emperor's alignment with heaven's rhythms. An unexpected eclipse, however, could trigger political crisis. Chinese astronomical instruments included more than just armillary spheres. They constructed gnomon towers for measuring the sun's shadow with precision, allowing them to determine the exact length of the solar year. Water clocks and mechanical devices track time with remarkable accuracy, essential for the precise timing required in astronomical work. Some of these instruments incorporated moving parts that mimicked celestial motions, creating mechanical models of the heavens that turned in synchronization with the actual sky. One particularly innovative astronomer named Zhang Heng, who lived during the 2nd century CE, created a seismoscope to detect distant earthquakes and constructed an elaborate water-powered armillary sphere that rotated automatically to match the sky's daily motion. His catalogue identified well over 1,000 stars, dividing them into constellations that reflected Chinese mythology and court life, rather than the animals and heroes of Greek tradition. The isolation of Chinese astronomy from Western developments for so many centuries created an independent check on celestial observations. When European missionaries finally brought Western astronomical knowledge to China in the 16th and 17th centuries, the extensive Chinese records provided confirmation for many events and revealed observations that had gone unrecorded in the West. Those ancient notations of guest stars and comets, carefully preserved through dynasties and upheavals, offered modern astronomers windows into cosmic events that occurred centuries before telescopes existed. As we prepare to journey westward again in our story, toward the Islamic scholars who would preserve and enhance Greek astronomical learning through centuries of cultural transformation, we carry with us an appreciation for how human curiosity about the heavens expressed itself in such varied yet equally sophisticated ways across the ancient world. The Chinese stargazers, working in their imperial observatories with bronze instruments and silk star maps, pursued the same cosmic questions that occupied minds in Alexandria and Athens, adding their own invaluable contributions to humanity's growing understanding of the universe above. As the astronomical traditions of China continued their independent flowering in the East, a different preservation and transformation of knowledge was unfolding across a vast expanse of territory, stretching from Spain to Central Asia. The Islamic Golden Age, spanning roughly from the 8th to the 14th centuries, became a crucial bridge in the story of astronomy, a period when the science of the stars not only survived, but flourished with renewed vigor. The story begins in the midst of tremendous cultural exchange. As Islamic civilization expanded, scholars encountered the astronomical works of ancient Greece, India, and Persia. Rather than simply accepting these inheritances unchanged, Islamic astronomers approached them with critical minds and careful hands. In the great libraries and houses of wisdom that arose in Baghdad, Damascus, Cairo, and Cordoba, translation became an act of scholarship in its own right. Greek texts that might otherwise have been lost to history found new life in Arabic translations, carefully rendered by scholars who often added their own commentaries and corrections. The House of Wisdom in Baghdad, established in the early 9th century, served as a focal point for this intellectual activity. Here, scholars gathered manuscripts from distant lands, translating works by Ptolemy, Euclid, and Aristotle into Arabic. But translation was merely the beginning. Islamic astronomers recognized inconsistencies and limitations in the works they inherited, and they set about improving upon them through observation and mathematical refinement. One of the fundamental contributions of Islamic astronomy was the construction of increasingly sophisticated observatories. These were not simple viewing platforms, but complex institutions housing large, precision instruments designed for accurate measurement. The observatory became a place where theory met practice, where the predictions of ancient texts could be tested against the actual movements of celestial bodies. Astronomers built enormous quadrants and sextants, devices that allowed them to measure angular positions with unprecedented precision. Some of these instruments were so large they were incorporated into the architecture of buildings themselves. Al-Battani, working in the late 9th and early 10th centuries, exemplified the observational rigor of this era. From his observatory in what is now Syria, he conducted careful measurements of the sun's apparent motion through the sky, producing solar tables of remarkable accuracy. His determination of the length of the solar year differed from the true value by merely a few minutes. He also refined measurements of the apparent sizes of the sun and moon, work that would prove valuable for predicting eclipses. His careful observations revealed that the position of the sun's apogee, the point in Earth's orbit where it appears farthest from the sun, had shifted since Ptolemy's time, a discovery that demonstrated the value of repeated observations across centuries. The stars themselves received meticulous attention during this period. Islamic astronomers compiled new star catalogues, improving upon the positions recorded in Ptolemy's Almagest. Abd al-Rahman al-Sufi, working in the 10th century, produced his Book of Fixed Stars, a comprehensive catalogue that not only listed star positions but included detailed descriptions of their brightness and colour. Al-Sufi's work introduced Arabic star names that we still use today: Betelgeuse, Rigel, Aldebaran, and many others carry names derived from his descriptions, linguistic reminders of this golden age embedded in our modern night sky. Mathematical innovation formed another pillar of Islamic astronomy. Scholars developed new computational techniques and refined trigonometry, creating tools that made astronomical calculations more efficient and accurate. They constructed detailed tables, reimagined in Arabic, that allowed astronomers and astrologers to predict planetary positions without repeating complex calculations from first principles. These tables incorporated improved values for orbital periods and planetary motions derived from centuries of accumulated observations. The astrolabe, though not invented by Islamic scholars, reached its highest development in their hands. This elegant instrument, which could solve problems related to time and position through mechanical analog computation, became both a practical tool and a work of art. Islamic craftsmen created astrolabes of breathtaking beauty, engraved with intricate geometric patterns, while maintaining precise functionality. An astronomer with a well-made astrolabe could determine prayer times, find the direction to Mecca, measure the height of mountains or buildings, and solve various problems of celestial geometry. Islamic astronomers also grappled with theoretical problems in Ptolemy's system. While they accepted the geocentric model that placed Earth at the center of the cosmos, they identified mathematical and philosophical difficulties in Ptolemy's use of the equant point, a geometric construction that violated the principle of uniform circular motion. Scholars like Nasir al-Din al-Tusi in the 13th century developed alternative models using combinations of circular motions, attempting to preserve the observational accuracy of Ptolemy's predictions while satisfying philosophical requirements about the nature of celestial motion. These models, known as the Tusi couple and related geometric devices, demonstrated sophisticated mathematical thinking and may have influenced later European astronomers, though the exact paths of transmission remain subjects of scholarly investigation. The observatory at Marageh, established in what is now northwestern Iran in the 13th century under the patronage of Hulagu Khan, represented the culmination of Islamic observational astronomy. Here, Al-Tusi gathered astronomers from across the Islamic world and beyond, creating an international research institution. The astronomers at Marageh had access to extensive instruments and compiled new observations, producing revised planetary tables and theoretical works that attempted to perfect the astronomical models of their predecessors. Later, in the 15th century, Ulugh Beg, a grandson of Timur and ruler of Samarkand, built another magnificent observatory. His particular passion for astronomy led him to construct an enormous sextant built into the ground, allowing measurements of stellar positions with exceptional precision. The star catalogue produced under his direction contained positions for over 1,000 stars, determined through fresh observations rather than merely copying ancient sources. Throughout these centuries, astronomical knowledge flowed along trade routes and through diplomatic exchanges. The same channels that carried spices, textiles, and precious metals also transmitted ideas and observations. When European scholars in the later Middle Ages and Renaissance began to rediscover classical astronomy, they often encountered it through Arabic translations and commentaries, enriched by the observations and refinements contributed during these intervening centuries. As the Islamic Golden Age gradually waned, the astronomical torch was being picked up in Europe, where scholars were beginning to question fundamental assumptions about the cosmos. The careful observations, refined instruments, and mathematical techniques developed by Islamic astronomers would provide essential tools for the revolutionary changes that lay ahead in the continuing human quest to understand the heavens. The 15th century drew to a close in a world where Earth stood firmly at the center of all creation, where the heavens revolved in crystalline spheres around humanity's home, and where the arrangement of the cosmos seemed as settled as any truth could be. Yet in a quiet corner of northern Europe, in the city of Torun, along the banks of the Vistula River, a child was born who would quietly, carefully, and irrevocably change everything humanity believed about its place among the stars. Nicholas Copernicus entered the world in 1473, the son of a merchant in a thriving trading city. His early life gave little hint of the revolution he would spark, though his path led him through the great universities of his age. He studied at Krakow, where he encountered astronomy and mathematics. He traveled to Italy, absorbing the learning of Renaissance centers at Bologna and Padua, studying law, medicine, and the humanistic revival of ancient texts. Throughout these years, he encountered the Ptolemaic system in all its elaborate glory, with its epicycles and equants, its complex machinery designed to explain the wandering paths of planets across the sky. Yet something troubled Copernicus about this ancient system. It worked, certainly. Astronomers could predict planetary positions with reasonable accuracy using Ptolemy's methods. But the system had grown increasingly complicated over the centuries, with adjustments upon adjustments, additional circles and mathematical devices added to match the observations. There was something, Copernicus felt, inelegant about it all. The universe, he believed, surely operated on simpler principles. In the quiet hours, perhaps in the tower of Frombork Cathedral, where he would later serve as a canon, Copernicus began to contemplate an idea that had briefly surfaced in ancient times, but had been set aside for nearly 2,000 years. What if Earth was not the center? What if the Sun, instead, held that central position, with Earth merely one planet among others, spinning through space in an annual orbit? The thought was not entirely without precedent. The ancient Greek astronomer Aristarchus had proposed such an arrangement, though his idea had found little support in the classical world. But Copernicus began to explore what would happen if this heliocentric arrangement were developed into a complete mathematical system. Slowly, carefully, over many years, he worked out the implications. The advantages revealed themselves gradually. If Earth orbited the Sun rather than standing still, the peculiar retrograde motions of the planet suddenly made perfect sense. When Mars appeared to move backward against the stars, it was simply because Earth, traveling on its own orbit, was overtaking the slower-moving outer planet. What had required elaborate epicycles in the Ptolemaic system emerged naturally from the heliocentric perspective. The orbital arrangement also explained why Mercury and Venus never strayed far from the Sun in our sky. They were inner planets, their orbits smaller than Earth's, forever constrained to appear near our star from our vantage point. Copernicus found that his sun-centered system required fewer circles and less mathematical complexity than Ptolemy's Earth-centered cosmos. The universe, arranged this way, possessed an elegant simplicity that appealed to his sense of harmony. The planets fell into a natural order by their distances from the Sun, and their orbital periods increased in a regular progression. There was something aesthetically satisfying, something almost musical, about the arrangement. Yet Copernicus remained cautious. He understood the magnitude of what he was proposing. Moving Earth from its central position challenged not merely astronomical tradition, but deeply held beliefs about humanity's place in creation. A moving Earth also raised difficult questions. If our world spun daily on its axis and raced annually around the sun, why did we feel no motion? Why were we not flung from the surface? Why didn't a stone dropped from a tower fall far to the west as Earth rotated beneath it? For years, Copernicus shared his ideas only with a small circle of correspondents. He wrote a brief outline called the Commentariolus, which circulated in manuscript form among scholars. Word of his heliocentric theory spread quietly through the astronomical community. Some found it intriguing as a mathematical device for calculation. Others recognized it as a potentially revolutionary new description of reality. As Copernicus aged, his supporters urged him to publish his complete work. A young mathematician named Georg Joachim Rheticus traveled to Frombork to study with the aging astronomer and became convinced of the theory's importance. Rheticus helped prepare the manuscript and encouraged its publication. Finally, after decades of refinement, Copernicus agreed to release his complete treatise. The book, titled De Revolutionibus Orbium Coelestium, or On the Revolutions of the Heavenly Spheres, was a substantial mathematical work that laid out the heliocentric system in full detail. Legend suggests that Copernicus received the first printed copy on his deathbed in 1543, though whether he was still conscious enough to see his life's work in print remains uncertain. The book included a preface, written anonymously by a theologian named Andreas Osiander, suggesting that the heliocentric system should be understood merely as a mathematical tool rather than a description of physical reality. This preface, added without Copernicus's knowledge or permission, perhaps helped the book avoid immediate controversy, though it also diluted the revolutionary claim that Earth truly moved. The immediate impact of De Revolutionibus was quieter than one might expect for such a revolutionary work. It was a technical treatise, dense with mathematics and geometric diagrams, accessible only to serious scholars. Astronomers studied it, used parts of it, debated its merits. Some adopted the heliocentric model as a calculating device while still believing Earth remained at rest. Others began to wonder if Copernicus might be describing the actual structure of the cosmos. The true revolution sparked by Copernicus would unfold over the following century as other astronomers built upon his foundation. But the essential step had been taken. The door had been opened to a new vision of the universe, one in which Earth, was no longer the unmoving center, but a planet among planets, journeying endlessly around the sun. The cosmos had been reimagined, and though it would take time for this new image to displace the old, there could be no returning to the ancient certainty that Earth stood forever still at the heart of all creation. The story now carries us northward to Denmark, in the latter half of the 16th century, where a nobleman with an unusual passion would transform the practice of astronomical observation forever. While Copernicus had reimagined the cosmos with mathematical elegance, the next great leap forward would come not from theory but from painstaking, meticulous observation of the actual heavens. Tycho Brahe was born into Danish nobility in 1546. a position that would grant him resources few astronomers could dream of. As a young man, he witnessed an eclipse that had been predicted by astronomical tables, and this moment of witnessing calculation become reality sparked something profound within him. Yet when he began making his own observations, he noticed something troubling. The existing tables of planetary positions were often wrong, sometimes by days or even weeks. If astronomy was to truly understand the heavens, it needed better data, much better data. In 1572, something extraordinary appeared in the evening sky. A brilliant new star blazed forth in the constellation Cassiopeia, so bright it could be seen even in daylight. This was deeply troubling to the prevailing wisdom of the time, which held that the heavens beyond the moon were perfect and unchanging. Tycho carefully measured the position of this new star night after night, searching for any parallax, any shift in position that would indicate it was a nearby phenomenon in Earth's atmosphere, or perhaps between Earth and the moon. He found none. This brilliant visitor existed in the realm of the fixed stars themselves, proving that the celestial sphere could indeed change. We know today that Tycho had witnessed a supernova, the explosive death of a distant star, though such understanding lay centuries in the future. This observation brought Tycho fame throughout Europe, and it also convinced him of something crucial. The instruments available to astronomers were simply not precise enough. If the cosmos was to reveal its secrets, someone needed to build better tools and use them with unprecedented care. King Frederick II of Denmark, impressed by Tycho's growing reputation, offered him an extraordinary gift in 1576. The king granted Tycho the island of Hven, located in the Sound between Denmark and Sweden, along with the funds to build whatever observatory he desired. What Tycho created there would be unlike anything the world had seen. He called his observatory Uraniborg, the castle of Urania, after the muse of astronomy. It was part palace, part laboratory, part workshop. The building itself was designed with astronomical precision, its walls aligned to the cardinal directions. Within its walls and in surrounding grounds, Tycho installed instrument after instrument, each one custom-built to his exacting specifications. He constructed massive quadrants for measuring the altitude of celestial objects, armillary spheres showing the celestial coordinate system, and great sextants for measuring angular distances between stars and planets. Some of these instruments were so large they required their own buildings. What made Tycho's instruments special was not just their size, but their precision. He understood that accuracy required attention to countless details. His quadrants and sextants were marked with finer divisions than previous instruments. He developed techniques to minimize the errors that crept into measurements. He understood that metal expanded and contracted with temperature, that instruments could warp over time, that every observation carried uncertainty that needed to be accounted for. Night after night, year after year, in cold and warmth, in clear skies and partial clouds, Tycho and his assistants observed. They tracked the positions of stars, creating a catalogue that would eventually include over 1,000 entries, each position measured with an accuracy of about 1 arc-minute, roughly 1/30th the width of the full moon. This might not sound impressive to modern ears, but it represented a 10-fold improvement over previous measurements and approached the theoretical limit of what human eyes could achieve without telescopic aid. But Tycho's greatest treasure was his observations of the planets, particularly Mars. Night after night, when Mars was visible, Tycho recorded its position against the background stars. He tracked its wandering path, its periods of retrograde motion, the subtle variations in its brightness. He did the same for Jupiter and Saturn, for Venus and Mercury, accumulating a mountain of data that recorded the precise dance of these wanderers across the sky. Interestingly, despite his revolutionary approach to observation, Tycho never fully accepted the Copernican system. Perhaps his noble birth made it difficult to dethrone Earth from its central position, or perhaps he found legitimate scientific objections. He noted that if Earth truly orbited the Sun, the nearby stars should show parallax, shifting their apparent positions as Earth moved from one side of its orbit to the other. His instruments detected no such shift, which in his mind argued against Earth's motion. He did not know that stars were so vastly distant that even his precise instruments could not detect their tiny parallactic movements. Instead, Tycho proposed his own hybrid model. In his system, the Sun and Moon orbited Earth, but all the other planets orbited the Sun. This preserved Earth's central position, while accounting for some of the mathematical advantages of the Copernican arrangement. It was a compromise between old and new, though history would ultimately judge it a transitional curiosity rather than a lasting contribution. In 1588, the death of King Frederick removed Tycho's royal patron. Relations with the new king, Christian IV, proved difficult. Tycho's arrogance and demanding nature had made him enemies, and by 1597, he had left Denmark entirely, taking his precious observations with him. He eventually settled in Prague under the patronage of the Holy Roman Emperor Rudolf II. It was in Prague that Tycho met a brilliant young mathematician named Johannes Kepler. Kepler desperately wanted access to Tycho's planetary observations, particularly the detailed records of Mars. Tycho, protective of his life's work and perhaps jealous of Kepler's theoretical gifts, granted access only grudgingly. The two men had a complex relationship, marked by mutual need and mutual frustration. When Tycho died suddenly in 1601, after a brief illness, his decades of precise observations passed into Kepler's hands. Tycho had spent his life gathering the raw material, but had never quite assembled it into a revolutionary new understanding. That task would fall to another. But without Tycho's patient accumulation of accurate data, the next great breakthrough in astronomy would have been impossible. As we drift towards sleep, we might picture those cold Danish nights. Tycho and his assistants peering through sighting tubes, carefully noting the exact position where a planet crossed a marked wire, recording numbers by lamplight. It was unglamorous work, demanding patience and dedication. Yet from those thousands of careful measurements, truth would eventually emerge, though Tycho himself would not live to see it. The treasure trove of precise observations that Tycho Brahe had so meticulously gathered would find its most brilliant interpreter in a young mathematician named Johannes Kepler. Born in 1571 in the small German town of Weil der Stadt, Kepler arrived at Tycho's observatory near Prague in 1600, bringing with him an exceptional mathematical mind and an almost mystical belief that the universe operated according to divine mathematical harmonies. The collaboration between these two men was brief but fateful. Tycho, the observational genius, possessed the most accurate planetary position, data the world had ever known. Kepler, the mathematical visionary, possessed the analytical tools to unlock the secrets hidden within those numbers. When Tycho died unexpectedly in 1601, Kepler inherited not only his position as imperial mathematician, but also access to those precious decades of observations. Kepler initially set himself what seemed a straightforward task: to work out the orbit of Mars using Tycho's data. He assumed, as nearly everyone still did, that planets moved in circular paths. The circle, after all, was considered the perfect shape, and the heavens were thought to be the realm of perfection. Even Copernicus, who had dared to move Earth from the center of the cosmos, had retained the ancient commitment to circular motion. What followed was nearly a decade of calculation, frustration, and eventually breakthrough. Kepler worked with extraordinary precision, refusing to ignore even the smallest discrepancies between theory and observation. When his circular models differed from Tycho's observations of Mars by merely 8 arc minutes, less than a quarter the width of the full moon, other astronomers might have dismissed such tiny errors as acceptable. Kepler could not. He trusted Tycho's observations implicitly and knew that those 8 arc minutes meant his model was wrong. In his struggle with Mars, Kepler filled page after page with calculations, trying variation after variation of circular orbits. He experimented with different speeds, different orientations, different combinations of circles within circles. He later described this period as his war with Mars. And indeed, it must have felt like a battle, him against the stubbornness of numbers that refused to align, against his own assumptions, against centuries of astronomical tradition. The breakthrough came when Kepler finally abandoned the circle entirely. Perhaps Mars moved not in a circle but in an oval, an ellipse. This was a radical thought, almost a scandalous one. To suggest that heavenly bodies traced imperfect paths seemed to diminish the divine order of creation. Yet when Kepler calculated an elliptical orbit for Mars, with the Sun positioned not at the center, but at one of the 2 focal points of the ellipse, the observations suddenly fell into place with beautiful precision. This discovery became Kepler's first law of planetary motion. Planets move in elliptical orbits with the Sun at one focus. It was published in 1609 in his work Astronomia Nova, or New Astronomy. The relief and triumph Kepler must have felt after his long struggle shines through in his writing, where he described his achievement with evident joy. But Kepler discovered something else in those years of calculation, another pattern hidden in Tycho's data. He noticed that planets did not move at constant speeds along their orbits. When a planet was closer to the Sun, it moved faster. When farther away, it moved more slowly. This variation was not random but followed a precise mathematical relationship. A line drawn from the Sun to a planet would sweep out equal areas in equal times. If you imagine this line tracing the planet's motion for 1 month when the planet was near the Sun, the wedge-shaped area it defined would be long and narrow. When the planet was far from the Sun, a month's motion would create a shorter, fatter wedge, but the area of both wedges would be identical. This became his second law, the law of equal areas. It provided a precise way to calculate where a planet would be at any given time, accounting for the variations in its speed throughout its elliptical journey. The implications were profound. The cosmos followed mathematical rules more subtle and beautiful than simple circular uniformity. Kepler did not stop there. His mind sought deeper harmonies, larger patterns that might unite all the planets in a single mathematical relationship. For years, he searched for what he called the music of the spheres, convinced that God had designed the solar system according to geometric and harmonic principles. Many of his ideas along these lines were fanciful, products of his mystical inclinations rather than observational evidence. But in 1619, after more than a decade of additional work, he discovered a third relationship that was genuine and profound. He found that there was a mathematical connection between how long a planet takes to orbit the Sun and how far it is from the Sun. Specifically, if you take the time for one complete orbit and square it, then take the average distance from the Sun and cube it. The ratio between these two numbers is the same for every planet. This relationship, now known as Kepler's third law, or the harmonic law, revealed that all the planets were indeed connected by a single mathematical principle. A planet twice as far from the Sun as another doesn't take twice as long to orbit. It takes longer still. Following this precise cubic relationship, this discovery meant that the solar system was not just a collection of separate objects, each following its own path, but an integrated system governed by universal mathematical laws. Kepler's three laws transformed astronomy from a discipline of geometric description into one of mathematical physics. He had shown that the actual paths and speeds of planets could be described with precision using relatively simple mathematical relationships. The cosmos, it turned out, operated not through complicated machinery of circles upon circles, but through elegant mathematical principles. What Kepler could not do was explain why planets followed these laws. He speculated about magnetic forces emanating from the Sun, pushing planets along their path. But he had no theory of gravity, no understanding of the physical mechanism that maintained these elliptical orbits. That synthesis would wait for another mind, another generation. But Kepler had provided the essential description of how planets actually moved, derived from painstaking analysis of the most reliable observations available. His work stands as a testament to the power of persistence, mathematical insight, and the willingness to abandon cherished assumptions when they conflict with careful observation. The perfect circles of ancient astronomy gave way to ellipses, and in that imperfection, a deeper perfection was found. The perfection of mathematical law, describing the actual motions of the heavens. As you drift towards sleep, perhaps you can imagine those elliptical paths, the planets sweeping through space at varying speeds, all connected by invisible mathematical threads, dancing to equations that Kepler first heard in the movements of Mars. The mathematics of planetary motion had revealed the elegant architecture of the heavens, but understanding the patterns and seeing them with one's own eyes were two entirely different experiences. As the 17th century dawned, A new instrument would transform astronomy from a discipline of careful measurement and calculation into one of direct observation and discovery. The telescope would open vistas that ancient astronomers could never have imagined, and no one would wield this new tool more dramatically than an Italian mathematician named Galileo Galilei. The telescope itself was not Galileo's invention. In the autumn of 1608, Dutch spectacle makers had discovered that combining lenses in a tube could make distant objects appear closer. News of this curious device spread across Europe like ripples on a pond. When word reached Galileo in Padua during the summer of 1609, his mind immediately grasped the possibilities. While others saw a novelty, or perhaps a military advantage, Galileo envisioned pointing such an instrument toward the night sky. With his knowledge of optics and considerable skill as a craftsman, Galileo set about improving the basic design. The early Dutch versions magnified objects only 3 or 4 times. Galileo refined the arrangement of lenses, experimented with different grinding techniques, and achieved magnifications of 8 times, then 20 times, and eventually 30 times. He worked in his studio, grinding and polishing glass, testing combinations, creating instrument after instrument in pursuit of clearer, sharper images. Each improvement brought the heavens closer to human eyes. On a clear evening in late 1609, Galileo turned one of his telescopes toward the moon. What he saw astonished him. The moon was not a perfect sphere of smooth, luminous material as Aristotelian philosophy had long maintained. Instead, its surface was rough and varied, marked by mountains and valleys. The boundary between light and shadow on the lunar surface appeared jagged and irregular. By observing how shadows changed as the moon moved through its phases, Galileo could even estimate the heights of lunar mountains, finding some as tall as mountains on Earth. This discovery alone challenged ancient assumptions, but it was merely the beginning. Night after night, Galileo explored the sky with his improved telescopes, and each session brought new wonders. When he observed the Milky Way, that diffuse band of light stretching across the darkness, his telescope resolved it into countless individual stars, too numerous to count, too faint to see with unaided eyes. The heavens contained multitudes beyond what anyone had suspected. In January 1610, Galileo turned his attention to Jupiter, that bright, wandering star the ancients had named for the king of the gods. On the 7th of that month, he noticed 3 small stars near the planet, arranged in a straight line. He noted their positions carefully. The following night, they had moved, but strangely, they remained close to Jupiter. More nights of observation revealed an astonishing truth. These were not stars at all, but smaller bodies orbiting Jupiter itself. A 4th such companion soon appeared. Here was a miniature planetary system, with Jupiter as its center, and these 4 moons revolving around it. The implications resonated deeply. If Jupiter could have moons circling it, while Jupiter itself moved through space, then not everything in the cosmos orbited Earth. The Ptolemaic insistence that Earth must be the center of all celestial motion had found a clear counterexample. Here was observable evidence that celestial bodies could orbit centers other than Earth, lending powerful support to the Copernican view of the cosmos. Galileo published these discoveries in a small book he titled Sidereus Nuncius, the Starry Messenger, in March 1610. The work created an immediate sensation. Here were not theoretical arguments or mathematical models, but things anyone with a telescope could see for themselves. Galileo described the lunar mountains, the multitude of stars and the moons of Jupiter with the excitement of an explorer reporting from a newly discovered continent. His observations continued. When Galileo examined Venus through his telescope over many months, he observed something that the geocentric model could not easily explain. Venus went through a complete set of phases, just like the moon, cycling from crescent to full and back again. Moreover, Venus appeared much larger when it showed a crescent phase than when it appeared full. In the Ptolemaic system, where Venus orbited between Earth and the Sun, the planet should never appear fully illuminated from Earth's perspective. But Galileo saw Venus in all phases, including full, which made sense only if Venus orbited the Sun, not Earth, sometimes appearing on the far side of the Sun and sometimes on the near side. The Sun itself revealed secrets through the telescope. Galileo observed dark spots on its bright surface, patches that appeared and disappeared over days and weeks. By tracking these sunspots, he demonstrated that the Sun rotated on its axis. Even the supposedly perfect, unchanging Sun bore markings and possessed motion. The Aristotelian distinction between a perfect, eternal celestial realm and an imperfect, changing earthly one seemed increasingly difficult to maintain. Galileo's telescopic discoveries did not immediately settle the debate between geocentric and heliocentric models. Many scholars still found the Ptolemaic system, refined over centuries, more persuasive than the Copernican alternative. Some refused to look through the telescope at all, dismissing the instrument as unreliable or its images as illusions created by the lenses. Others looked but interpreted what they saw differently, finding ways to reconcile the observations with Earth-centered models. Yet something fundamental had shifted. Astronomy had entered a new age where direct observation could reveal phenomena that previous generations never knew existed. The telescope had extended human vision far beyond its natural limits, and the cosmos, revealed through those improved lenses, appeared far richer and more complex than ancient philosophy had imagined. Mountains on the moon, moons around Jupiter, phases of Venus, spots on the Sun, countless stars invisible to the naked eye. Each discovery added detail and texture to humanity's picture of the heavens. The instrument itself would continue to improve. Later, astronomers would build longer telescopes, grind better lenses, and eventually develop reflecting telescopes using mirrors instead of lenses. Each improvement brought fainter objects into view and revealed finer details on celestial bodies. But it was Galileo who first demonstrated the telescope's power to transform astronomy, who first showed that looking directly at the heavens with enhanced vision could challenge theories and reveal unexpected truths. As the 17th century progressed, the observations Galileo pioneered would combine with the mathematical insights of Kepler to create an increasingly comprehensive understanding of planetary motion. Yet one fundamental question remained unanswered. What force or principle caused planets to follow their elliptical paths? What invisible influence kept moons circling Jupiter and planets orbiting the Sun? The answer to that question would require insights not just about the heavens, but about motion, force, and gravity itself. The observations that Galileo shared with the world had opened a new window onto the heavens, but they had also opened a profound question. If the moon orbited Earth, and moons orbited Jupiter, and planets circled the sun, what invisible force held these celestial bodies in their paths? What kept the planets from simply flying off into the darkness of space? And what prevented them from falling into the sun? The telescope had revealed the cosmic dance, but the music that orchestrated these movements remained mysterious. In England, a young man of extraordinary mathematical ability had been pondering questions of motion and force. Isaac Newton, born in the small village of Woolsthorpe in 1642, the same year that Galileo died, possessed a mind uniquely suited to unraveling the mathematical secrets of nature. During his student years at Cambridge, he had already begun developing new mathematical techniques that would later become calculus, though he kept these discoveries largely to himself, working in relative solitude. When the plague swept through England in 1665, Cambridge University closed its doors, and Newton returned to his family's modest manor house in Lincolnshire. There, in the quiet countryside, removed from the bustle of academic life, his thinking flourished. He contemplated the nature of light, of colors, and of motion. The question of what kept the moon in orbit around Earth particularly captivated him. He understood that something must constantly pull the moon toward Earth, preventing it from traveling in a straight line, as moving objects naturally tend to do. Newton realized that this pull might be the same force that caused an apple to fall from a tree to the ground. Whether the famous story of the falling apple is literal truth or later embellishment, it captures an essential insight. Newton recognized that the force pulling objects downward on Earth's surface might extend outward through space, reaching the moon itself, the planets, and beyond. Gravity, he proposed, was not merely an earthly phenomenon, but a universal force acting between all objects that possess mass. The mathematical description of this force emerged through years of careful thought. Newton proposed that every object in the universe attracts every other object with a force proportional to the product of their masses, and inversely proportional to the square of the distance between them. This inverse square relationship meant that gravity weakened rapidly with distance. Doubling the distance reduced the force to 1/4 its original strength, but it never disappeared entirely. The gravitational influence of every star extended throughout the cosmos, growing fainter, but never reaching zero. This elegant mathematical law had profound implications. Newton could use it to explain why Kepler's planets moved in elliptical orbits. The mathematics showed that an object moving under the influence of an inverse square force naturally traces out an ellipse, with the source of the force at one focus, exactly as Kepler had discovered through painstaking analysis of observational data. The three laws that Kepler had extracted from Tycho Brahe's measurements were not merely empirical patterns, but inevitable consequences of universal gravitation. Newton's law also explained the motion of projectiles on Earth, the ocean tides influenced by both moon and sun, and the precession of Earth's axis. It predicted that comets moved in elongated elliptical paths around the sun, making regular returns rather than traveling through the solar system just once. When Edmund Halley, a younger astronomer and friend, used Newton's methods to predict that a particular comet would return in 1758, its appearance on the schedule, 16 years after Halley's death, provided dramatic confirmation of the theory's power. The presentation of these ideas came in one of the most important scientific works ever written. At Halley's urging and financial support, Newton published the Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy, in 1687. The Principia, as it became known, laid out the fundamental laws of motion and the law of universal gravitation with mathematical rigor, written in Latin and expressed in geometric proofs rather than the calculus Newton had privately developed. It was not an easy book to read, but its arguments were compelling and comprehensive. The Principia established 3 laws of motion that governed all movement in the universe. The first stated that objects in motion remain in motion, and objects at rest remain at rest, unless acted upon by a force. The second quantified how forces change motion, establishing the relationship between force, mass, and acceleration. The third declared that for every action, there exists an equal and opposite reaction. These principles, combined with universal gravitation, provided a complete framework for understanding mechanical phenomena both on Earth and in the heavens. Newton's achievement represented a profound unification. Before the Principia, celestial mechanics and earthly physics had been treated as separate domains, governed by different principles. Aristotle had taught that the heavens operated according to perfect, unchanging laws quite unlike the imperfect, changeable realm beneath the moon. Newton demonstrated that the same laws applied everywhere. The force that shaped the path of a thrown stone on Earth was identical in nature to the force that guided planets in their orbits. The universe operated according to consistent mathematical principles that human reason could comprehend. This mathematical universe proved remarkably predictive. Astronomers could now calculate planetary positions with unprecedented accuracy, accounting for the subtle gravitational influences that planets exerted on one another. When observations occasionally diverged from predictions, astronomers suspected unseen planets whose gravity caused the discrepancies. This approach would later lead to the discovery of Neptune in 1846, found almost exactly where calculations predicted an unknown planet should exist to explain irregularities in Uranus's orbit. Newton's framework dominated physics and astronomy for more than 2 centuries. Scientists applied his laws to an ever-expanding range of phenomena, from the stability of Saturn's rings to the dynamics of binary stars. The deterministic universe he described operated like an intricate clockwork, its future states determined by mathematical laws acting on present conditions. Given the position and velocity of every particle in the universe, one could in principle calculate all future configurations, a vision of complete predictability that would later be challenged by quantum mechanics and chaos theory, but which represented the pinnacle of Enlightenment scientific thinking. Yet Newton himself remained modest about his achievements. In his later years, he compared himself to a boy playing on the seashore, finding a smoother pebble or prettier shell than ordinary, while the great ocean of truth lay undiscovered before him. He had revealed fundamental principles governing cosmic motion, but he acknowledged mystery remained. He could describe how gravity acted mathematically, but could not explain what gravity actually was. What mechanism allowed distant objects to influence each other across empty space? As the night sky wheels overhead in its ancient patterns, we can appreciate how Newton's insights transformed those patterns from mysterious phenomena into understood mechanics. The same principles that govern the fall of rain and the arc of a bird's flight extend outward to shape the orbits of worlds, binding the cosmos together with invisible threads of gravitational force, creating order and predictability in the vast darkness of space. With Newton's mathematical framework illuminating how gravity governed the dance of planets and moons, astronomers now possess the tools to understand celestial mechanics with remarkable precision. Yet one fundamental question remained tantalizingly difficult to answer. Just how far away were the stars themselves? The night sky presented a brilliant tapestry of light, but whether these distant suns hung just beyond Saturn's orbit or resided at incomprehensible distances remained a mystery that would require both technical ingenuity and patient observation to solve. The challenge was deceptively simple to state, but extraordinarily difficult to accomplish. If astronomers could measure the apparent shift in a star's position as Earth traveled from one side of its orbit to the other, they could use basic geometry to calculate the star's distance. This stellar parallax, as it became known, represented a cosmic version of holding your thumb at arm's length, and alternately closing each eye to watch it appear to jump against the background. Earth's orbit provided the baseline for this measurement, with observations 6 months apart offering the maximum separation between viewing positions. The problem was that even the nearest stars were so distant that their parallax shifts proved almost impossibly small to detect. Throughout the 17th and 18th centuries, skilled observers attempted to measure stellar parallax with increasingly sophisticated instruments. Each failure told them something profound. The universe was even larger than they had imagined. The absence of detectable parallax didn't mean the method was flawed. It meant the stars were extraordinarily far away. Among those who pursued this elusive measurement was James Bradley, an English astronomer who in the 1720s turned his telescope toward a star called Gamma Draconis. Night after night, he carefully noted its position, hoping to catch the telltale back-and-forth motion that would reveal its distance. Bradley did indeed detect a shift in the star's apparent position, but the pattern puzzled him. The movement didn't match what parallax should produce. After careful analysis, Bradley realized he had discovered something entirely unexpected: the aberration of starlight. Because Earth moves through space as it orbits the Sun, and because light travels at a finite speed, starlight appears to come from a slightly different direction depending on Earth's motion, much like falling rain appears to slant toward you when you walk through it. This discovery confirmed that light had a finite speed and provided new evidence of Earth's motion. But it wasn't the parallax measurement Bradley had sought. The stars, it seemed, remained too distant for even his precise instruments to measure their parallax. The quest continued into the 19th century. William Herschel, whose telescopic surveys would later revolutionize understanding of our galaxy's structure, attempted to use double stars for parallax measurements. His reasoning was clever. If two stars appeared close together in the sky, but were actually at different distances, the nearer one should show a larger parallax shift against its more distant companion. Though Herschel's attempts didn't yield the measurements he hoped for, his observations of double stars revealed that many were true binary systems, stars bound together by gravity and orbiting their common center of mass. As the 1830s arrived, telescope technology and measurement techniques had finally advanced sufficiently to make stellar parallax detectable. The race was on among several astronomers to be the first to successfully measure this cosmic distance. In Königsberg, Friedrich Wilhelm Bessel selected a star known as 61 Cygni for his attempt. This star wasn't among the brightest in the sky, but Bessel chose it for a different reason. It had a large, proper motion, meaning it moved noticeably against the background stars over time. This suggested it might be relatively nearby, making its parallax potentially larger and easier to detect. Using a specialized instrument called a heliometer, Bessel made painstaking measurements throughout 1838. The heliometer allowed him to measure tiny, angular separations with unprecedented precision. Month after month, he tracked 61 Cygni's position relative to two fainter background stars. Gradually, a pattern emerged from his data. The star did indeed shift back and forth, tracing a tiny ellipse in the sky as Earth completed its annual journey around the Sun. When Bessel announced his results, he had measured a parallax of approximately 1/3 of an arcsecond. To appreciate how small this angle is, imagine dividing a single degree into 3,600 equal parts, then taking one of those parts and dividing it into 3. The entire width of a full moon spans roughly 1,800 arcseconds. Bessel was measuring stellar positions to a fraction of an arcsecond, detecting shifts smaller than a coin viewed from several miles away. This tiny angle translated into an enormous distance. Using the geometry of triangulation with Earth's orbit as his baseline, Bessel calculated that 61 Cygni lay approximately 600,000 times farther from us than the Sun. Light itself, traveling at its tremendous speed, required more than 10 years to cross the gulf between that star and Earth. The universe had suddenly acquired measurable depth, and that depth was staggering. Almost simultaneously, other astronomers achieved similar successes. Thomas Henderson at the Cape of Good Hope measured the parallax of Alpha Centauri, which turned out to be even closer than 61 Cygni, though Henderson delayed publishing his results. Friedrich von Struve in Russia measured the parallax of Vega. Within months, 3 stellar distances had been determined, opening a new era in astronomy. These measurements transformed astronomy from a science of angles and positions to one that could describe the three-dimensional architecture of space. Stars were no longer points of light fixed to a celestial sphere, but distant suns scattered through an immense volume, each at its own unique distance. The cosmos had acquired depth and scale that dwarfed anything previously conceived. As more stellar distances were measured, astronomers began to recognize patterns. They noticed that stars of similar appearance could have vastly different true brightnesses once their distances were known. A dim-appearing star might simply be distant, while a brilliant-appearing one might be intrinsically luminous. By comparing apparent brightness with true distance, astronomers could begin to calculate the actual luminosity of stars, revealing an astonishing diversity in stellar power. These distance measurements also allowed astronomers to determine the true motions of stars through space. Proper motion showed how stars moved across our line of sight, but now radial velocities measured through spectroscopy could be combined with distance to construct three-dimensional pictures of stellar movements. The stars weren't fixed at all, but traveled through space on their own journeys, their apparently permanent patterns slowly shifting over millennia. The techniques pioneered by Bessel and his contemporaries could only reach the nearest stars. Most stars remained too distant for parallax measurement with 19th century instruments. Yet the principle was established. and the cosmic distance ladder had its first rung. As you drift towards sleep, imagine those patient observers, night after night, measuring infinitesimal angles, transforming specks of light into distant suns, and finally comprehending the true vastness of the stellar realm that surrounded our small world. As we had learned to measure the distances to nearby stars, a more profound question began to occupy the minds of astronomers in the late 18th and early 19th centuries. What was the true nature and extent of that luminous band stretching across the night sky that we call the Milky Way? Was it simply a local cluster of stars? Or did it represent something far grander? Perhaps the fundamental structure of the stellar universe itself? William Herschel, the German-born musician turned astronomer working in England, approached this question with characteristic determination and methodical precision. Unlike many of his contemporaries who focused on individual celestial objects, Herschel conceived an ambitious project to survey the entire visible sky, counting and cataloguing stars in every direction. With his sister Caroline by his side as both assistant and accomplished astronomer in her own right, Herschel embarked on what he called star gauging, systematically counting stars in different regions to determine the distribution and structure of the heavens. Using telescopes of his own construction, including instruments with mirrors that were the largest and finest of their era, Herschel spent countless nights under the English sky, methodically sweeping from one region to another. He would count the number of stars visible in his telescope's field of view, then move to another section and count again. Over years of patient observation, he accumulated thousands of these measurements, building up a statistical picture of how stars were distributed across the celestial sphere. From this painstaking work, a shape began to emerge. Herschel noticed that stars appeared far more numerous along the band of the Milky Way than they did in directions perpendicular to it. He reasoned that if the sun resided within a flattened disk of stars, observers would naturally see more stars when looking along the disk's plane than when looking up or down from it. In 1795, he published his conclusions about the shape of what he called the starry stratum, a vast, irregular disk of stars with the sun positioned somewhat near its center. The picture Herschel painted was of a stellar system shaped rather like a grinding stone or millstone, wide and flat, with ragged edges. He estimated its dimensions, though his measurements would later prove to be far too modest. Still, this was revolutionary. The first serious attempt to map the architecture of our stellar system from within. For the first time, astronomers were not simply cataloguing what they saw in the sky, but trying to understand the three-dimensional structure of the cosmos itself. Yet even as Herschel mapped what he could see, puzzling objects appeared in his surveys that didn't quite fit. Scattered among the crisp points of stars were fuzzy patches of light called nebulae, from the Latin word for cloud. Some appeared as faint, diffuse glows. Others showed hints of spiral structure. The great question was, what were these mysterious objects, and where did they reside? Herschel himself went back and forth on this question throughout his life. Some nebulae, he thought, might be clouds of luminous gas or fluid within our own star system. Others, he speculated, might be distant collections of stars, perhaps other Milky Ways, separate island universes scattered through infinite space. The limits of his telescopes, however, could not resolve the question definitively. The nebulae remained tantalizingly ambiguous, neither clearly within nor obviously beyond our stellar realm. As the 19th century progressed, larger telescopes revealed more detail in these nebulous objects. The third Earl of Ross, William Parsons, constructed a massive telescope in Ireland with a 6-foot diameter mirror. Through this Leviathan instrument, he observed the spiral structure of certain nebulae with unprecedented clarity, sketching the beautiful whirls of what we now know as galaxies like Messier 51. Yet even this impressive instrument could not settle whether these spirals were nearby clouds or distant star systems. The debate became one of the central questions in astronomy. Were nebulae simply parts of our own stellar system, perhaps stars in the process of formation from condensing clouds? Or were they separate galaxies of stars beyond the boundaries of the Milky Way? Astronomers split into two camps. Some believed the Milky Way encompassed all that existed, that our galaxy was, in effect, the entire universe. Others held that the spiral nebulae represented separate galaxies, making the cosmos far vaster than the Milky Way alone. The challenge was one of measurement. To determine whether a nebula lay within or beyond our galaxy, astronomers needed to know its distance. But the nebulae were so far away that parallax measurements, which had succeeded for nearby stars, proved utterly useless. The nebulae showed no detectable shift in position as Earth orbited the Sun. They were simply too distant, whether they lay at the far reaches of our galaxy or in the depths of intergalactic space. Throughout the latter half of the 19th century and into the 20th, the question remained unresolved. Astronomers mapped the Milky Way's extent as best they could, but estimates varied wildly. Some placed the Sun near the center of the galaxy, while others argued for a more peripheral position. The true scale remained maddeningly uncertain, hidden by the limitations of both observation and theory. What observers could see clearly, however, was that the Milky Way was not uniformly bright. Dark patches and lanes cut through the luminous band, creating rifts and gaps in the stellar glow. Some astronomers interpreted these as genuine voids, regions where no stars existed. Others, more presciently, suggested that dark clouds of obscuring matter might block the light of stars beyond. This interstellar material, if it existed, would complicate any attempt to gauge the true extent and shape of our galaxy by visual observation alone. As the 19th century gave way to the 20th, astronomers stood at a threshold. They knew they inhabited a vast collection of stars, flattened into a disk-like structure. They had catalogued thousands of nebulous objects, some clearly gaseous clouds, others mysteriously spiral in form. But the fundamental question remained open. Did the Milky Way represent the entire universe? Or was it merely one galaxy among countless others, scattered through an incomprehensibly vast cosmos? The tools to answer that question were beginning to emerge, and the resolution would transform our understanding of existence itself. For now, on the edge of discovery, astronomers could sense that the universe might be far stranger and larger than even the boldest imagination had dared to suggest. The light from distant stars had traveled across unimaginable gulfs of space to reach human eyes, carrying within it secrets that astronomers had only begun to suspect. By the middle of the 19th century, the mystery of what stars were actually made of seemed forever beyond human grasp. The French philosopher Auguste Comte had declared in the 1830s that humanity would never know the chemical composition of celestial bodies. The stars were simply too far away, too remote from any earthly laboratory. Yet even as he wrote these words, the very tool that would prove him wrong was being developed. The key arrived in the form of a simple glass prism. When light passes through such a prism, it spreads into a rainbow of colors, a phenomenon that had delighted observers since ancient times. But in the early 1800s, a German optician named Joseph von Fraunhofer noticed something peculiar while examining sunlight split by his prisms. The solar spectrum was not a smooth, continuous rainbow. Instead, it was crossed by hundreds of dark lines, like mysterious gaps in the colors. Fraunhofer carefully mapped these lines, labeling the most prominent ones with letters. He had no idea what caused them, but his meticulous documentation would prove invaluable. The explanation emerged gradually through the work of multiple researchers, Robert Bunsen and Gustav Kirchhoff, working in Heidelberg in the 1850s, heated various chemical elements to incandescence and examined the light they produced through spectroscopes, refined instruments designed specifically for analyzing light. Each element they discovered produced its own characteristic pattern of bright lines at specific colors. Sodium always produced two bright yellow lines very close together. Hydrogen created a series of lines, including a prominent red one. Every element had its own unique spectral fingerprint. The connection to Fraunhofer's dark lines became clear through further experiments. When light passed through a cooler gas containing a particular element, that gas absorbed light at precisely the same wavelengths where it would emit bright lines if heated. The dark lines in the solar spectrum were absorption lines, created when light from the sun's hot interior passed through cooler gases in its outer atmosphere. Those gaps in the rainbow were actually a code, spelling out the chemical composition of the sun itself. Astronomers realized they held in their hands a tool of extraordinary power. Every star in the sky was broadcasting information about its chemistry through its light. What had seemed an impossible dream, knowing what distant suns were made of, became a practical endeavor. Spectroscopes were attached to telescopes, and observers began the patient work of capturing and analyzing starlight. The findings were remarkable. The same elements found on Earth appeared in stellar spectra: hydrogen and calcium and iron and dozens more. The universe was made of the same substance as our world. This fundamental unity seemed both humbling and profound. Stars were not composed of some ethereal celestial material, but of ordinary matter. The same atoms that formed rocks and rivers and human bodies. William Huggins in England became one of the pioneers of stellar spectroscopy, beginning his observations in the 1860s. Working from his private observatory with spectroscopes he designed himself, Huggins examined star after star, nebula after nebula, carefully recording the patterns of lines. He discovered that some nebulae showed the bright line spectra characteristic of glowing gas, while others showed continuous spectra-like stars, suggesting they might be vast collections of stars rather than clouds. The spectra revealed more than just chemistry. They also encoded information about motion. Christian Doppler an Austrian physicist, had predicted in the 1840s that the wavelength of light from a moving source would be shifted, compressed if the source approached the observer, stretched if it moved away. This Doppler effect, as it came to be known, meant that spectral lines from an approaching star would be shifted slightly toward the blue end of the spectrum, while lines from a receding star would shift toward the red. Huggins achieved the first measurement of a star's radial velocity in 1868, determining that Sirius was moving away from Earth. The shift was tiny, requiring careful measurement and comparison with laboratory spectra, but it was detectable. Stars no longer hung motionless in the heavens. They had velocities that could be measured, three-dimensional motions through space that added a new dimension to astronomical study. As spectroscopy advanced, astronomers began noticing that stars showed different types of spectra. Some showed strong hydrogen lines. Others showed prominent lines from metals. Some spectra appeared relatively simple, while others bristled with hundreds of absorption features. At first, the diversity seemed bewildering, but gradually patterns emerged. In the 1870s and 80s, astronomers developed classification schemes, grouping stars by their spectral characteristics. The Italian astronomer Angelo Secchi organized stars into several classes based on their spectra. This system was refined and expanded by astronomers at Harvard College Observatory, where a team of dedicated women researchers, including Williamina Fleming, Antonia Mori, and Annie Jump Cannon, examined and classified the spectra of hundreds of thousands of stars. Cannon developed the classification sequence that became standard, arranging stellar spectra in a sequence designated by the letters O, B, A, F, G, K, and M. Generations of astronomy students would memorize this sequence using mnemonics, learning that these letters represented a continuous sequence of stellar types. What this sequence actually meant took time to understand. Different spectral types did not represent different chemical compositions so much as different temperatures. The hottest stars, the O and B types, shone blue-white and showed relatively simple spectra, dominated by ionized helium and hydrogen. Cooler stars like our Sun, a G-type, showed more complex spectra with many metallic lines. The coolest M stars glowed red and showed molecular absorption bands from compounds that could only exist at relatively low temperatures. Spectroscopy provided a new way to classify and understand stars, to organize the bewildering diversity of the stellar population into a coherent framework. The temperature sequence became a fundamental organizing principle. Combined with measurements of stellar brightness, spectral classification would eventually help astronomers understand the life cycles of stars themselves, though that synthesis still lay in the future as the 19th century drew to a close. The gentle rain of starlight, properly analyzed, told stories about stellar chemistry, temperature, pressure, and motion. Information that had traveled for years or centuries across the depths of space could be decoded by patient observers with their prisms and photographic plates. The spectroscope transformed astronomy from a science of positions and motions into a science of physical understanding. The stars remained distant, but they were no longer silent. Their light spoke volumes to those who learned to listen, revealing a cosmos more complex and more comprehensible than astronomers had dared to imagine. As the 19th century gave way to the 20th, astronomers had assembled a magnificent toolkit for understanding the heavens. Spectroscopy had revealed the chemical composition of distant stars. Mathematical laws described the motions of planets with exquisite precision, and telescopes brought ever fainter celestial objects into view. Yet beneath this edifice of knowledge, subtle cracks had begun to appear. Certain observations refused to align with established theory, and in the quiet offices and laboratories where physicists pondered the fundamental nature of reality, a revolution was brewing that would transform not only astronomy, but our entire conception of the cosmos itself. At the heart of this revolution stood a young patent clerk in Bern, Switzerland, a man whose name would become synonymous with genius itself. Albert Einstein, working in relative isolation from the academic mainstream, had been contemplating problems that had puzzled physicists for years. The nature of light, the meaning of simultaneity, the relationship between space and time. These abstract questions occupied his thoughts as he reviewed patent applications by day and filled notebooks with calculations by night. In 1905, a year that would later be called his miracle year, Einstein published a series of papers that shook the foundations of physics. Among these was his theory of special relativity, which proposed something deeply counterintuitive: that space and time were not absolute and independent entities, but were woven together into a unified fabric that behaved in unexpected ways. According to Einstein's mathematics, two observers moving relative to one another would disagree about measurements of distance and duration. Time itself could slow down for a rapidly moving object, and lengths could contract along the direction of motion. For astronomers, the implications seemed modest at first. After all, planets and stars moved at speeds far below that of light, where these relativistic effects would be negligible. But Einstein's equations also revealed something profound about the nature of mass and energy, captured in perhaps the most famous equation in all of physics. Energy and mass were equivalent, related by the square of the speed of light, a conversion factor of staggering magnitude. This simple relationship would later help explain how stars could shine for billions of years, burning mass itself as fuel through nuclear fusion. Yet Einstein was not satisfied. Special relativity described how the laws of physics appeared to observers moving at constant velocities relative to one another. But it said nothing about acceleration or gravity. For the next decade, Einstein struggled with what he called the happiest thought of my life, the realization that a person falling freely experiences no gravity. From this simple insight, he began to construct a far more ambitious theory. General Relativity, published in 1915, reimagined gravity not as a force reaching across empty space, but as a consequence of space-time's geometry itself. Massive objects like stars and planets create curves and dimples in the fabric of space-time, and other objects moving through this curved landscape follow the straightest possible paths through the warped geometry. A planet orbiting the Sun travels in an ellipse not because an invisible force pulls it, but because the Sun's mass has shaped the very structure of space and time around it. And the planet simply follows the natural contours of this curved space-time. The mathematics Einstein developed to express these ideas was formidable, employing sophisticated geometry that few physicists of his era had mastered. The equations were beautiful, but complex, and even Einstein himself struggled to extract predictions from them. Yet within months of publication, he had calculated 3 observable consequences that could test his theory against Newton's older conception of gravity. The first was subtle. A tiny additional rotation in Mercury's orbit that Newton's laws could not fully explain. Astronomers had long known that Mercury's elliptical path slowly rotated over time, a precession that could mostly be accounted for by the gravitational influences of other planets. But a small discrepancy remained. A mere 43 seconds of arc per century that had resisted all conventional explanation. When Einstein applied his field equations to Mercury's orbit, out came precisely this missing rotation, with no adjustable parameters or ad hoc assumptions. The theory explained a lingering mystery naturally and elegantly. The second prediction was more dramatic. Light itself, Einstein proposed, should be affected by gravity. A beam of starlight passing near the sun would be deflected by the sun's gravitational field, or more precisely, would follow a curved path through the warped space-time surrounding the solar mass. The deflection would be small, only detectable for stars appearing very close to the sun's edge as seen from Earth. During an ordinary day, the sun's brilliance would drown out these stars entirely. But during a total solar eclipse, when the moon blocked the sun's disk, stars near the sun's limb could be photographed, and their positions compared to measurements made when the sun occupied a different part of the sky. The opportunity to test this prediction came in 1919, just after the conclusion of the Great War. A British expedition led by Arthur Eddington travelled to the island of Principe off the coast of West Africa, while another team went to Sobral in Brazil, both positioned along the path of totality for a solar eclipse occurring in May. Despite clouds and technical difficulties, the observers captured photographic plates during the brief minutes of totality. When analysed back in England, the stellar positions showed precisely the deflection Einstein had predicted. Space itself bent in the presence of mass, guiding light along curved paths. The announcement of these results made Einstein an international celebrity virtually overnight. Here was confirmation of a theory so strange, so far removed from everyday intuition, yet validated by careful observation. Newspapers around the world proclaimed that Newton had been overthrown, though in truth Einstein's theory encompassed Newton's as a special case, valid when gravitational fields were weak and velocities low. The third prediction was perhaps the most subtle. General relativity suggested that time itself runs at different rates, depending on the strength of the gravitational field. Clocks deep within a gravitational well tick more slowly than clocks farther away from massive objects. This gravitational time dilation was too small to measure with the technology of Einstein's day, but it implied something profound. Gravity was not just a warping of space, but a warping of time as well. For astronomers and cosmologists, general relativity opened entirely new avenues of thought. If space-time could be curved by mass and energy, what did this mean for the universe as a whole? Could the entire cosmos have a geometry, a shape? Might the universe be finite yet unbounded, curved back upon itself, like the surface of a sphere exists in 2 dimensions? Einstein himself attempted to apply his equations to the universe as a whole, though the answers he found troubled him in ways that would only become clear in later years. The theory also predicted exotic possibilities that seemed almost like science fiction. Sufficiently compact masses might curve space-time so severely that nothing, not even light, could escape. Objects that would later be called black holes. The equations allowed for gravitational waves, ripples in space-time itself, propagating outward from accelerating masses at the speed of light. And under certain conditions, massive objects could act as gravitational lenses, their curved space-time focusing light from more distant sources, potentially creating multiple images of a single distant star. As astronomers absorbed these revolutionary ideas, they realized they had been given not just a new theory of gravity, but an entirely new framework for understanding the cosmos. The universe revealed by general relativity was dynamic, geometric, and stranger than previous generations had imagined. Space and time were not merely the stage on which cosmic events unfolded. They were active participants in the drama, shaped by matter and energy, influencing the paths of everything within them. The heavens that humanity had studied for millennia had suddenly become far more mysterious and wonderful, awaiting explorers equipped with Einstein's mathematical compass to chart their curved and flowing geometries. The universe that Albert Einstein's equations had revealed was one of curved space-time and gravitational phenomena that bent and shaped the cosmos in ways previous generations could scarcely have imagined. Yet even as these revolutionary ideas were being absorbed by the scientific community, another transformation was quietly taking shape at Mount Wilson Observatory in California, where a young astronomer named Edwin Hubble was turning the magnificent 100-inch Hooker telescope toward the night sky. In the early 1920s, astronomy faced a fundamental question that had puzzled observers for generations. Scattered across the heavens were mysterious spiral nebulae, cloud-like structures that appeared in even modest telescopes as fuzzy, indistinct patches of light. Some astronomers believed these nebulae were clouds of gas within our own Milky Way galaxy, relatively nearby phenomena swirling among the familiar stars. Others suspected something far more extraordinary, that these spiral forms might be separate galaxies entirely, vast collections of stars so distant that they appeared as mere smudges of light, island universes scattered throughout an inconceivably larger cosmos. The debate had raged for years, coming to a head in 1920 during what became known as the Great Debate, when astronomers Harlow Shapley and Heber Curtis presented opposing views at the National Academy of Sciences. Shapley argued that the spiral nebulae lay within our galaxy, while Curtis proposed they were external galaxies. Both men marshaled evidence, but neither could provide the definitive measurement that would settle the question once and for all. Edwin Hubble possessed the tool that could finally resolve this cosmic mystery. The Hooker telescope, with its enormous light-gathering power, could reveal details in these distant nebulae that smaller instruments simply could not capture. Hubble began a systematic study of the Andromeda Nebula, the largest and brightest of the spiral nebulae visible from Earth. Night after night, he photographed this celestial object, creating images that captured its delicate spiral arms with unprecedented clarity. Within these photographs, Hubble searched for individual stars, hoping to identify a particular type known as Cepheid variables. These remarkable stars had been studied extensively by Henrietta Swan Leavitt, who had discovered a precise relationship between how bright a Cepheid truly is and how rapidly it pulsates. This relationship meant that by measuring a Cepheide's period of variation, an astronomer could determine its actual luminosity. Comparing this true brightness with how bright the star appeared from Earth revealed its distance through a straightforward calculation. In October 1923, Hubble's patience was rewarded. Among the stars he had been tracking in Andromeda, he identified a Cepheid variable. His careful measurements of its brightness variations, combined with Leavitt's period luminosity relationship, yielded a stunning result. The Andromeda Nebula lay approximately 900,000 light-years away, far beyond the boundaries of the Milky Way galaxy. This single observation proved that Andromeda was indeed a separate galaxy, a collection of hundreds of billions of stars so distant that the entire structure appeared as a faint smudge to the unaided eye. The implications were staggering. The known universe expanded dramatically in that moment. Humanity's cosmic home was not the entirety of creation, but rather one galaxy among many. As Hubble identified Cepheids in other spiral nebulae, measuring their distances one by one, the picture became ever clearer. Galaxies populated space in all directions, each one a massive congregation of stars separated from its neighbors by distances that dwarfed anything previously contemplated. But Hubble was not finished reshaping our understanding of the cosmos. As he measured distances to these galaxies, he also examined their light through spectroscopes, instruments that spread starlight into its component colors. Other astronomers, particularly Vesto Slipher at Lowell Observatory, had already noticed something peculiar about the spectra of spiral nebulae. The characteristic patterns of dark lines that appeared in their light were systematically shifted toward the red end of the spectrum, suggesting that these objects were moving away from Earth. Hubble began comparing the distances he had measured with the velocities indicated by these redshifts. What emerged from this comparison was one of the most profound discoveries in the history of science. The farther away a galaxy was, the faster it appeared to be receding. This relationship was not random, but followed a clear pattern. Velocity increased proportionally with distance. A galaxy twice as far away was moving away twice as fast. The implications of this simple linear relationship were revolutionary. The universe was not static and unchanging, as had been assumed for millennia. Instead, space itself was expanding, with galaxies rushing away from each other as the very fabric of the cosmos stretched. This expansion meant that galaxies appeared to recede from us in all directions, but not because we occupy a special position. Rather, any observer in any galaxy would see the same pattern, as the expansion of space carries all galaxies away from all other galaxies. This discovery, announced in 1929, fundamentally altered humanity's conception of the universe. The cosmos had a dynamic character, evolving and changing over time. If galaxies were moving apart now, then in the distant past they must have been closer together. Tracing this expansion backward in time suggested that the universe had a beginning, a moment when all matter and energy occupied an incredibly small space. The static, eternal universe gave way to one with a history, a story of expansion and evolution spanning billions of years. The constant of proportionality that Hubble measured, relating velocity to distance, would come to bear his name. The Hubble constant became one of the most important numbers in cosmology, a value that describes the present rate of cosmic expansion and provides a means to estimate the age of the universe itself. Though Hubble's initial measurements would later be refined and corrected, the fundamental relationship he discovered remains the cornerstone of modern cosmology. In just a few years, Edwin Hubble had transformed our understanding of the universe not once but twice. First, he had revealed that our galaxy was just one among multitudes, populating a cosmos far larger than previously imagined. Then, he showed that this vast universe was not frozen in time, but rather expanding, carrying galaxies along on a cosmic journey that began in the distant past and continues into an open future. As astronomers absorbed these revelations, they began to contemplate the mechanisms that powered the stars themselves, the processes that allowed these brilliant points of light to shine across the vast distances Hubble had measured, bringing information about distant galaxies to our waiting telescopes. With the vast universe of galaxies now spread before humanity's understanding, astronomers turned their attention to a question that had flickered in human imagination since the first campfires cast dancing shadows in the night. What were the stars themselves? How did they come to shine with such steadfast brilliance? And what journeys did they undertake across the immense spans of cosmic time? The answer would reveal itself gradually, like dawn breaking across a dark landscape, as astronomers in the early 20th century began to piece together the remarkable life stories written in starlight. These were narratives spanning millions and billions of years, tales of birth and transformation and eventual death that played out on scales almost impossible to grasp. Yet through patient observation and careful reasoning, the biographical details of stellar existence began to emerge from the data. In the 1920s and 1930s, astronomers made a curious discovery when they plotted stars according to their brightness and color. The Danish astronomer Einar Hertzsprung and the American Henry Norris Russell independently created diagrams that revealed unexpected patterns. Most stars fell along a diagonal band stretching from their hot, bright blue stars to cool, dim red ones. This main sequence, as it came to be called, suggested something fundamental about how stars worked. But other stars scattered across different regions of the diagram, enormous red giants and tiny white dwarfs, hinted that stellar existence involved more than simply shining steadily in one configuration forever. The key to understanding these patterns lay in nuclear physics, a field that was itself just emerging into the light of scientific understanding. In the late 30s, Hans Bethe worked out the nuclear reactions that powered the Sun and other stars, deep within stellar cores, where temperatures soared to millions of degrees and pressures crushed matter to extraordinary densities. Hydrogen atoms fused together to form helium. This process released tremendous energy, the energy that had warmed Earth and illuminated the cosmos for billions of years. Stars were not burning in any conventional sense, not consuming fuel through chemical reactions, but rather transforming matter itself through the alchemy of nuclear fusion. This insight opened the door to understanding stellar evolution. A star begins its life in clouds of gas and dust floating through the galaxy, regions where matter slowly gathers under its own gravitational attraction. As these clouds collapse and fragment, dense cores form and heat up through compression. When the central temperature reaches about 10 million degrees, hydrogen fusion ignites and a star is born. The outward pressure from nuclear reactions balances the inward pull of gravity, creating a stable equilibrium that can last for millions or billions of years, depending on the star's mass. Our own sun has shone steadily on the main sequence for about 4.5 billion years, fusing hydrogen into helium at a rate that converts millions of tons of matter into energy every second. Yet the sun is a star of middle age and moderate mass, and its future holds transformations that astronomers came to understand by studying other stars at different life stages. When a star exhausts the hydrogen in its core, the story takes a new turn. Without fusion to support it against gravity, the core contracts and heats up. This allows hydrogen in a shell around the core to begin fusing, releasing more energy than before. The increased energy output pushes the star's outer layers outward, causing the star to swell into a red giant. The surface cools and reddens even as the overall luminosity increases enormously. In several billion years, our sun will undergo this transformation, expanding until it perhaps engulfs the inner planet, becoming a red beacon in Earth's sky if Earth survives at all. For stars of modest mass like our sun, the core eventually becomes hot enough to fuse helium into carbon and oxygen. This provides a new lease on fusion life, though a much briefer one than the long hydrogen burning phase. When the helium-2 is exhausted, stars like the Sun lack the mass to compress their cores to the temperatures needed for further fusion. The outer layers drift away into space, creating beautiful planetary nebulae, those gossamer shells of glowing gas that astronomers photograph in colors of ethereal beauty. What remains is the hot, dense core, a white dwarf star roughly the size of Earth, but containing more than half the original star's mass. White dwarfs gradually cool over billions of years, eventually fading to darkness. They represent the final chapter for stars of low to moderate mass, a quiet ending to lives that may have spanned 10 billion years or more. The matter in white dwarfs is supported not by fusion or thermal pressure, but by quantum mechanical effects. The same principles that prevent electrons from occupying the same quantum state. This degeneracy pressure, as physicists call it, holds the white dwarf against further collapse. But more massive stars follow different and more dramatic paths. Stars with several times the Sun's mass burn through their fuel much more quickly, living perhaps only millions of years rather than billions. They also achieve higher core temperatures that allow fusion to continue beyond helium burning. Carbon fuses into heavier elements, then oxygen, then silicon, building up an onion-like structure of shells where different fusion reactions occur. This process continues until the core becomes iron. Iron, positioned at the peak of nuclear binding energy, cannot release energy through fusion. When enough iron accumulates, disaster strikes suddenly. Without energy generation to support it, the iron core collapses catastrophically in less than a second, compressing to nuclear densities. The collapse rebounds in a tremendous explosion called a supernova, briefly outshining an entire galaxy. The outer layers of the star blast into space at speeds of thousands of kilometers per second, enriching the interstellar medium with the heavy elements forged in the star's interior and in the explosion itself. Every atom of carbon, oxygen, and iron in your body was created inside stars and dispersed by stellar death. We are, quite literally, made of star stuff, as Carl Sagan would later eloquently observe. What remains after a supernova depends on the original star's mass. For some, a neutron star forms, an object about 20 kilometers across, yet containing more mass than the Sun. Neutron stars are supported by neutron degeneracy pressure, essentially one giant atomic nucleus. Some rotate rapidly, sweeping beams of radiation across space like cosmic lighthouses, pulsars that can tick with extraordinary precision. For the most massive stars, even neutron degeneracy pressure cannot halt the collapse. The core continues contracting until it becomes a black hole, a region where gravity warps space-time so severely that not even light can escape. These objects, predicted by general relativity and once considered mathematical curiosities, gradually became accepted as real denizens of the cosmic landscape. This understanding of stellar life cycles emerged through decades of work combining observation, physics, and theoretical modeling. It explained the patterns in the Hertzsprung-Russell diagram and revealed stars as dynamic objects with histories and destinies. The night sky became a portrait gallery displaying stars at every stage of life, from stellar nurseries glowing with the light of newborn suns to the fading embers of white dwarfs cooling toward darkness. As astronomers traced these stellar biographies, they also came to understand cosmic recycling. The universe began, as they would discover, with primarily hydrogen and helium. Everything heavier was forged in stellar furnaces and supernova cauldrons, then scattered to form new generations of stars and eventually planets and people. The story of stars became inseparably linked to the story of matter itself and to our own origins, connecting the life cycles of distant suns to the very atoms from which we are made. With the life stories of stars now understood, astronomers found themselves contemplating an even more profound question. If stars had beginnings and endings, what about the universe itself? Could the entire cosmos have a birth, a history, and perhaps even a destiny? The answer would emerge through a combination of theoretical insight and observational detective work that ranks among humanity's greatest intellectual achievements. The story begins in the early decades of the 20th century, when astronomers noticed something peculiar in the light from distant galaxies. As we learned when spectroscopy opened new windows on the stars, light carries information not just about composition, but about motion. When an object moves away from us, its light shifts toward the red end of the spectrum, stretched like the changing pitch of a receding train whistle. Galaxy after galaxy showed this redshift, suggesting they were rushing away from us through space. In 1927, a Belgian priest and physicist named Georges Lemaitre proposed something remarkable. If galaxies were moving apart, then logically, they must have been closer together in the past. Following this reasoning backward through time, Lemaitre suggested that the entire universe must have begun in what he called a primeval atom, an incredibly dense state from which everything expanded. It was a radical idea that the universe had not existed forever, but had emerged from an explosive beginning. Around the same time, the Russian mathematician Alexander Friedmann had been exploring the equations of Einstein's general relativity. He discovered that these equations allowed for a universe that changed with time, either expanding or contracting. Einstein himself had been so convinced the universe must be static and eternal that he had added a special term to his equations, what he called the cosmological constant, to keep his mathematical universe from changing. When the evidence for expansion became undeniable, Einstein would reportedly call this addition his greatest blunder. The observational confirmation came through Edwin Hubble's careful measurements of galaxy distances and velocities. He discovered a relationship that now bears his name. The farther away a galaxy, the faster it appeared to be receding. This wasn't because galaxies were flying through space away from some central point. Rather, space itself was expanding, carrying galaxies along like raisins in a rising loaf of bread. Every point was moving away from every other point as the fabric of space stretched. Yet many scientists remained skeptical of this new picture. The British astronomer Fred Hoyle championed an alternative called the steady state theory, which proposed that the universe had no beginning but existed eternally, with new matter constantly being created to fill the gaps as space expanded. Ironically, it was Hoyle who, during a 1949 radio broadcast, dismissively referred to the competing theory as the Big Bang, a name that stuck despite its somewhat comical sound. For years, these two visions competed. The steady state theory had an appealing elegance, avoiding the thorny question of how everything could suddenly spring into existence. But the Big Bang theory made predictions that could be tested. If the universe began in an incredibly hot, dense state and then expanded and cooled, there should be remnants of that primordial heat, still detectable today. In 1948, physicist George Gamow and his colleagues Ralph Alpha and Robert Herman worked out what the early universe must have been like. In the first minutes after the Big Bang, when the cosmos was unimaginably hot, protons and neutrons would have fused into the lightest elements. Their calculations predicted the proportions of hydrogen and helium we should find in the universe today. More importantly, they predicted that the radiation from this hot early phase should still fill the universe, cooled by expansion to just a few degrees above the absolute zero. For years, this prediction lay dormant, almost forgotten. Then, in 1964, two radio astronomers at Bell Telephone Laboratories in New Jersey made an accidental discovery that would change everything. Arno Penzias and Robert Wilson were testing a sensitive radio antenna, trying to eliminate all sources of unwanted noise. No matter what they did, a persistent hiss remained in their data, coming equally from all directions in the sky. They even cleaned out pigeons nesting in the antenna, thinking their droppings might be the culprit, but the mysterious signal persisted. Meanwhile, just down the road at Princeton University, physicist Robert Dick and his team were preparing to search for the very radiation that Gamow had predicted. When Penzias and Wilson heard about this work, the pieces suddenly fell into place. That annoying hiss they had been trying to eliminate was nothing less than the afterglow of creation itself, the cosmic microwave background radiation that had been traveling through space for nearly 14 billion years. This discovery provided overwhelming evidence for the Big Bang theory. Here was the fossil radiation from the universe's infancy. cooled from billions of degrees to just 2.7 degrees above absolute zero by the expansion of space itself. Penzias and Wilson received the Nobel Prize in Physics for their discovery, though they had stumbled upon it quite by accident, while looking for something else entirely. The cosmic microwave background opened new avenues of investigation. This ancient light came from a time roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral atoms. Before this moment, free electrons scattered light in all directions, making the universe opaque like a thick fog. After this recombination, light could travel freely, and that's the radiation we detect today as the cosmic microwave background. Astronomers realized this ancient light contained information about the early universe encoded in tiny temperature variations across the sky. Studying these patterns could reveal how matter was distributed in the young cosmos, how the first structures began to form, and what fundamental parameters governed the universe's evolution. Missions like NASA's Cosmic Background Explorer satellite in the 1990s and the Wilkinson Microwave Anisotropy probe in the 2000s mapped these variations with exquisite precision. From these observations and many others, a detailed history of cosmic origins emerged. The universe began 13.8 billion years ago in a state of extraordinary density and temperature. In the first fraction of a second, it underwent a period of exponential expansion called inflation. As it expanded and cooled, the fundamental forces separated, particles formed, and the simplest atomic nuclei emerged. Hundreds of thousands of years later, atoms formed and light could travel freely. Hundreds of millions of years after that, the first stars ignited, and gradually the universe organized itself into the cosmic web of galaxies we see today. This understanding represented a triumph of both observation and theory, of patient measurement and bold mathematical reasoning. Humanity had traced the history of everything back to its beginning, had measured the age of the cosmos itself, and had glimpsed the conditions of its birth. As astronomers continued to refine these measurements and push their observations to greater distances and earlier times, new questions inevitably emerged, new mysteries waiting in the darkness between the stars. As the 20th century drew to a close and a new millennium began, astronomy underwent yet another transformation. This time through technologies that would have seemed like pure fantasy to earlier generations of stargazers. The instruments that now probe the cosmos extend far beyond what human eyes can perceive, gathering whispers of light and other signals from the most distant reaches of space and time. The decision to place telescopes above Earth's atmosphere marked a pivotal shift in observational capability. On April 24, 1990, the Space Shuttle Discovery carried the Hubble Space Telescope into orbit, positioning this remarkable instrument where atmospheric turbulence could no longer blur the light from distant stars and galaxies. Though initial problems with the mirror required a dramatic repair mission, the corrected Hubble soon began returning images of unprecedented clarity and beauty. The telescope's deep field observations, pointing at seemingly empty patches of sky for days at a time, revealed thousands of galaxies in regions where ground-based telescopes saw only darkness. Each galaxy contained billions of stars, and these images came from light that had traveled for much of the universe's lifetime to reach the waiting detector. Hubble's successors expanded these capabilities even further. The James Webb Space Telescope, launched on Christmas Day 2021, positioned itself nearly 1 million miles from Earth, where its enormous mirror and infrared sensitivity allow it to peer through cosmic dust clouds and observe the universe's first galaxies forming in the distant past. These space-based observatories work alongside ground-based telescopes of remarkable sophistication, their adaptive optics constantly adjusting mirror shapes to counteract atmospheric distortion, achieving clarity that rivals viewing from space. Yet visible light represents only a narrow slice of the electromagnetic spectrum, and modern astronomy has learned to listen to the universe across all its frequencies. Radio astronomy, which began almost accidentally when Carl Jansky detected radio emissions from the Milky Way in 1933, has become a powerful tool for exploring phenomena invisible to optical telescopes. Massive radio dishes and arrays of interconnected antennas map the structure of gas clouds, trace the spiral arms of distant galaxies, and detect the rapid spinning of pulsars, those lighthouse-like remnants of massive stars. The Very Large Array in New Mexico links 27 radio dishes, while the Atacama Large Millimeter Array in Chile uses 66 antennas working in concert to observe wavelengths between radio and infrared, studying the cold dust clouds where stars are born. X-ray and gamma-ray observatories have revealed a violent and energetic universe invisible to optical telescopes. The Chandra X-ray Observatory, an XMM Newton satellite, detect high-energy radiation from superheated gas falling into black holes, from the remnants of supernova explosions, and from the collisions of galaxy clusters. These observations unveil processes occurring at extreme temperatures and densities, phenomena that push matter and energy to their limits. Perhaps no recent development has captured public imagination quite like the discovery of planets orbiting other stars. For centuries, astronomers could only speculate about whether our solar system was unique, or whether planets accompanied other suns. The first confirmed detection of an exoplanet orbiting a sun-like star came in 1995, when Michel Mayor and Didier Queloz found a Jupiter-sized world in a surprisingly tight orbit around the star 51 Pegasi. This discovery opened floodgates of planetary detection. The Kepler Space Telescope, launched in 2009, monitored over 150,000 stars simultaneously, watching for the tiny dimming that occurs when a planet crosses in front of its star. Kepler's observations revealed that planets are remarkably common throughout our galaxy, with many stars hosting multiple worlds. The variety of planetary systems discovered has been astonishing, from hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, to compact systems of multiple rocky planets, to worlds orbiting binary stars under two suns. The TESS mission continues this work, surveying the entire sky for planets around the nearest and brightest stars, while ground-based instruments use the subtle wobble that planets induce in their parent stars to detect even more distant worlds. Among the thousands of exoplanets now catalogued, astronomers have begun identifying worlds that orbit within their star's habitable zone, where temperatures might allow liquid water to exist on a planetary surface. These potentially Earth-like worlds have become targets for intense study. with future telescopes designed to analyze their atmospheres for signs of water vapor, oxygen, methane, and other gases that might indicate not just habitability, but perhaps even life itself. The universe has also begun speaking to us in an entirely new language, one predicted by Einstein, but only recently heard. On September the 14th, 2015, the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, detected ripples in space-time itself, gravitational waves produced by the collision of two black holes more than 1 billion light-years away. This observation opened an entirely new window on the cosmos, allowing astronomers to witness events that produce no light at all. Additional detections have followed, including the collision of two neutron stars that was observed both through gravitational waves and across the electromagnetic spectrum, from gamma rays to radio waves, providing a comprehensive view of one of nature's most energetic events. Yet for all these remarkable discoveries, modern astronomy has also revealed how much remains mysterious. Observations of galaxy rotation and gravitational lensing indicate that the luminous matter we can see accounts for only a small fraction of the total mass in the universe. The rest, termed dark matter, reveals itself only through gravitational effects, its nature remaining one of astronomy's greatest puzzles. Even more puzzling is the discovery that the universe's expansion is accelerating, driven by something dubbed dark energy that appears to make up nearly 70% of the universe's total energy content. The nature of this dark energy remains deeply mysterious, a humbling reminder that our understanding of the cosmos remains incomplete. Modern astronomy has become a collaborative, worldwide endeavor, with data flowing freely between observatories on every continent and in space. Automated surveys scan the entire sky repeatedly, alerting astronomers within seconds when something changes or appears, whether a supernova explosion in a distant galaxy or an asteroid passing near Earth. The field has evolved from individual astronomers spending cold nights at telescope eyepieces to large teams analyzing data streams from automated instruments using powerful computers to process information far beyond human capacity to examine manually. As we conclude this long journey through the history of astronomy, from ancient eyes tracking celestial patterns to gravitational wave detectors, listening to space-time itself, we find ourselves in an age of unprecedented cosmic awareness. We know our address in a universe containing hundreds of billions of galaxies. We understand how stars forge the elements that make up our world and ourselves. We can trace cosmic history backward to mere fractions of a second after the Big Bang, and we search for signs of life on worlds circling other suns. Yet with each answer, new questions emerge, and the cosmos continues to surprise us. The story of astronomy is far from finished. New instruments now being planned and built will peer even deeper into space and time, and discoveries yet unmade await in data already collected or in observations still to come. The ancient human impulse to look upward and wonder continues, now amplified by technologies that extend our senses across the entire electromagnetic spectrum and beyond, as we continue learning to read the universe's stories written in light, in gravity, and in the very fabric of space and time itself. As we bring to a close our journey through the vast story of astronomy, from ancient civilizations gazing upward in wonder to our modern understanding of galaxies, stars, and the cosmic dance that surrounds us. We hope these stories have gently carried you through the evening. Thank you for joining us on this peaceful exploration of the heavens. If these calm adventures have brought you comfort, we'd love to have you with us again. Like, subscribe, and share your thoughts in the comments below to help other smart sleepers find their way here. And now, as the night deepens and your mind settles like stardust finding its place in the universe, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.